Okay. I was sitting there. I was like, well, right before you got on, I was sitting there. I was like, okay. Normally people start checking in right about now, and then I heard the ding dong, and I was like, all right, cool. And then
Maybe the wall loops blew up everybody's brains yesterday.
I don't know.
So I don't know. Yeah. Oh, there we go.
There we go. Okay, good.
Oh, were you guys waiting on me?
Well,
we weren't
everybody,
sure.
we were like, did we miss something?
Oh, well, it's not quite 8 o'clock yet. I would.
You know, as it gets later and later in the training, people were like,
I was actually trying to work on some code, but I wanted to do it in private because I wasn't able to get it to work. So.
Yeah, I feel that.
Yep. Speaking of code working, want to see the video of Josh's? Well, I guess we can wait till everyone gets on. Oh, I might need to get access to it.
Yeah, just request, and I'll give you access. I thought I didn't set. Never mind. I probably didn't set access to it.
Yep. I think I just requested access. You know, for a second there, I was thinking it was Friday, but no, it's only Thursday.
That's weird. It's not asking if I.
See, 8 o'clock, everyone's hopping on. Do I need to request again, or?
It's not popping up.
It says request sent. You'll get an email letting you know if your request was approved.
I wonder if it's sending it. Oh, there it is.
Oh. Turn on some more lights.
You should have it now.
Okay. Okay. Let's see here. I guess. Okay. We've got a bunch of people here. Yeah, before we look at Josh's video, I guess we should share the word for today. Today's word's going to be bumper. Bumper is going to be our word for today. Well, someone just joined, so maybe you should. Oh, Lisa popped on twice. Okay, one of those are a cell phone. Okay. Lisa, if you didn't hear, today's word is bumper. I'm assuming you're saying things because your mouth are moving.
I could hear, but I just couldn't see.
Oh, okay.
Trinity throws today, doesn't she?
Yes.
Cool. Tell her good luck.
All right.
Yeah, that sounds exciting.
Yeah, she made nationals for javelin at LSU.
Wow. Well,
That's very cool.
So it's got to be what, 5 o'clock in the morning where you are in Oregon?
Yes.
Is that how time zones work? Is it really?
Well, no, it's actually almost 6 now. Probably it might be 6 now.
Yeah, I got up at 5:30 to get here.
That's dedication. You are dedicated, ma'am.
Yep. Okay. So everyone got the word bumper. So Josh actually filmed his. He filmed this code and he wanted to share it with us. So one thing I could do, because streaming a video over Zoom is probably, so I can share maybe the link to the Google Drive of the video too. And I'll put that in the chat, and you might have to do some more permissions there, Jess. Well, I guess I'll do screen share as well. But where is my where's the chat? Okay, there it is. Sorry. I'm not quite thinking very well this morning. That is not what I want to post in chat. I want to post this link in chat. I guess Josh could have posted this link in chat. Think about it, because he sent the link to me. But this is the link to Josh's video. So in case I'll play it here, but you know how streaming from a stream. So this might look choppy to you guys. So that's him going forward 2 feet, backing up 2 feet, raising the arm and lowering the arm. Going forward should be 4 feet. And he's got it showing on the brain and backing up 4 feet.
Yeah, I realized after the fact that I forgot to, once I got through the 2 forward, 2 back in the shot, I meant for it to go all the way back to the top. So I cleared screen, but I forgot to reset it to 1. And
yeah.
And so I went back and fixed the code after that. I didn't reshoot it though.
Yeah. But yeah, so what he's talking about, see it on the screen, the text is kind of moving down. So you have to set I think it's set position, I think, or maybe not set position.
Yeah, I did. Well, that's what I did. I did set position. I did 1-1. Yeah.
Yeah, and then I'll put it back to the top. But that's looking really good. It's going straight.
I think mine did that, but it kept pulling to the left really hard. And
was it pulling to the left really hard when it was backing up, or
no, going forward?
When it was going forward, it was pulling to the left really hard.
Yeah. But it's almost like sometimes the wheel would turn, but sometimes it wouldn't. So it's probably something that I've done to it. I don't know. But anyway, it kept running into stuff, but it would raise the arm and lower it. And then I think it would have traveled the right amount of feet.
Yeah, if the axle is slipping out and causing the wheel not to spin, the robot's not going to know that.
Right. I think that's some of my problem.
Yeah.
Because I fixed one wheel, and then I think I'll probably have to fix the other one too. But anyway.
Yeah, and probably the most common mechanical error is going to be that axle slipping out. It's kind of one of the most annoying ones to deal with too. That's why for the usually I don't let the kids use the metal axle collars too much because one, that little tiny set screw in those axle collars is really, really easy to lose. And you need a different wrench for it too, like the smaller diameter wrench. But since it's so tiny, those get lost pretty easily. You can buy just the set screws for those things for relatively cheap off the Vex site. I think you can get like a pack of 50 for like a couple of bucks.
Oh, okay.
So yeah, if you're losing a set screw, but that metal, holding that metal axle collar to keep that axle in is probably one place where I would recommend letting the kids use those metal axle collars, because the rubber ones aren't. I mean, the rubber ones will prevent the axle moving a little bit, but not entirely. Whereas you've really got it like screwed in with the metal axle collar, they'll kind of prevent the axle from moving around a bit.
And you can also make it like a best practices to teach them to always like take your little collar and like push it in toward the motor before you run every time, just to make sure it's a nice tight fit. I learned that the hard way.
Yeah, that collar doesn't work if it's not like against the metal, because if there's any sort of play at all, it's gonna move. Also, that's also a reason why I recommend when you're using putting the black inserts, the one that they're usually used on the wheels and the gears, those black inserts, you can put those in the motors too. And that just gives the axle a little more space to grip on. So, but yeah. So how did everyone else do with theirs? Like, Miranda, did yours work okay, or?
I wrote the code and I didn't have any errors. I still have to put the arm back on, and I had to bring my mom to the doctor yesterday. So my goal is to today, like, actually run it on the robot, but I think the code writing went pretty well.
Mm-hmm. And you don't have to like physically have the arm on, as long as there's a motor attached to run, it will. Yeah.
I kind of want to see it do it, so
Yeah.
I just have to have a few minutes to get that done, but that's my plan today.
Okay. And then what else was I going to say? Well, and it is true that although the code looks like it might be right, you won't really know for sure until you run it. Because, like, for instance, and it was my bad yesterday, but we really, when we were writing our if statements, we really should have included the absolute value of our positions, like our left motor position and our right motor position, not just using a left and right motor position. And Josh kind of learned the hard way about that, because like we were talking about yesterday, it was going forward just fine. But when we're going backwards, since we weren't taking the absolute value of those positions, then the signs were getting kind of flipped. Like our inequalities were backwards because we were now dealing with negative numbers, and so but if we had just taken the absolute value of everything to begin with, we wouldn't have to worry about the inequalities flipping around. So, and then that kind of led us into, like, we really, before copy and pasting a lot of things, you probably should go ahead and test that section is working on the robot before, because now you're left with a whole bunch of things to change instead of just fixing that one thing. And that kind of leads us in today. We're going to learn about writing a function, because we wrote a whole lot of code just to kind of go forward, and a whole lot of code to go backwards. And if we had put all that code into a function, and then instead of having to copy and paste it every time and having like hundreds and hundreds of lines of code, we could have just put all that code in a function that we create, and then we could have just called on that function anytime we wanted to use it. And that's kind of what we're going to be learning about today. Today's lesson is Unit 9. And it's going to be about, and let me just make sure that is today's stuff. So today is Thursday. Yeah, Unit 9 content, Unit 10 content. That's what we're looking at today. So we're going to be looking at Unit 9, which is about the functions and the bumper sensor. There's also a little bit about building like a conveyor belt too, but that if you don't have the part, like for instance, we're going to be building kind of a Roomba type thing. And one thing you can kind of do to the Roomba is you can have the kids actually build like a conveyor or some sort of accumulator to pick up stuff while it's kind of going around. However, you do not really have to do that, especially if you're running short on time. You can just have them mount a bumper to the front of their robot and just like bump into things and back up. You don't necessarily have to do the part where But if you have the time to do it, that's just another fun building thing. The kids like building a lot more than they do the programming. So them actually building some sort of conveyor can be kind of fun for them. So I'm gonna share my screen if you guys don't know. But before we do, did any of you guys like look at the Unit 8 homework at all, or the Unit 8 quizzes? And did you guys have any questions about any of that content? No.
I started looking at it, but I didn't get to finish, so I need to play catch up.
Okay. Yep. So we did look a little bit at that Unit 8 homework yesterday. We looked at the truth table part of it. You might remember. But yeah, if you guys run any questions about any of that, we can answer any questions. Because we have our final coming up in a few days, in Tuesday. So we'll only have like another few days on this. But look how far we've come. We're already on Unit 9. Some, especially for first year teachers, some schools only get to Unit 9 and then don't really go any further than that. In fact, like Unit 10 and Unit 11 are kind of considered optional units, but recommended units. Well, at least Unit 10 is, because everyone should have access to either an ultrasonic sensor or a rangefinder. But that Unit 11, the vision sensor, not every school has vision sensors, so that can be kind of left off. And honestly, those last two units, I don't think are as fleshed out as well as some of the other units.
I had a quick question too.
Yes.
I can't remember if it explicitly said it in any of the slides or anything, but a while loop is always looking for a false, and an if loop or if statement's always looking for a true. Isn't that how, or one way you can differentiate them?
Well, that's not exactly. That's not really well, because a while loop is looking for a false to kick out of the loop.
Yeah, that's what I meant. Yeah.
But an if statement, you can think if it's false, it's also kicking out of the if, because it's not doing the if it's false.
I thought the while loop is continually checking. And
yes, it's
the if statement is like, okay, this didn't, or like, it's like, if this is, then you go to like, it's like a series of events.
Yeah. Because an if statement, an if statement only checks once, while a while loop checks over and over and over again.
I guess I meant to perform an action or to stop an action. I guess maybe I should have been more clear. Like an if statement is looking for a true to perform an action, and a while loop, I guess, is looking for a false to be done with the action.
Yeah, because it's just technically also looking for a true to perform that action, but it's just going to keep on performing that action because it's just going to keep on checking. And so there are a lot of situations where you want to be checking. Okay, and one thing to be very careful of is to not do like loops inside of loops. Very well. There are some situations where you might want to do a loop inside a loop, but usually you don't. Because oftentimes if you're putting a loop inside a loop, you can be trapped inside that inner loop and not be doing all the things, maybe other things that you want to do that's in the bigger loop, if that makes sense. So like for instance, sometimes it's maybe a good idea to make like a big master loop, and it could be like a continuous loop, like it is just by like while true. And then you can have like all kinds of if statements inside that master loop to do all kinds of different things or check all kinds of different things. But they're all just contained within that one master loop. And so, like for instance, that's kind of like when you're doing a drive program to drive around the robot. It's all in a one big master loop, uh, and then inside that, it's grabbing like the joystick value so it's checking that what the controller position is, uh, and then it's also like doing things like checking to see if buttons are being pressed or not, and then it's like doing actions based off of that. But those are all kind of like ifs and stuff like that. Like if the button's being pressed, and I'm going to raise the arm, and else if the other button's being pressed, I'll lower the arm. Else, I'm not going to do anything to the arm. And that thing kind of thing's going on. And meanwhile, you might also have another set of ifs, like if this button's being pressed, then I'll open the claw, and if this button's being pressed, I'll close the claw. Um, else I'll leave the claw alone. And so you'll have all those ifs kind of going on, all within the same loop. Yep. Um, so I was actually trying to write. So we're going to be introducing functions today, and I was actually trying to write a master function for just doing our movement, our auto straight movement. But I wanted to kind of write it in such a way that I could feed in whether it was going forward or backward or not. So, um, but I was having trouble with that. Like I was trying to pass that parameter along, that forward parameter along, but but it doesn't look like VEX code has string as a variable type. Uh, like because every time I try to do, because I was trying to store that word forward as a string, um, but it wasn't taking string as a variable type. So since I couldn't store forward, and then I couldn't use forward later when I was doing like my spin function, or I can store it as a variable. And I'm still haven't resolved that issue. uh, so
Instead of
that's what.
doing it as a string, could you just save it as like a character? Like to where like you're just using instead of a word forward, using like another substitution for that? I don't know.
Um, there's got to be a way to do it. But I don't know if character is a variable. So like if I try, I'll share my screen. Share, share, share. So like for instance, string in C, string is a variable type, but in this VEX code, see how it didn't light up blue? It just stayed black. And so like for instance, if I said string maybe dir for direction, and I set it equal to forward, if I try to build this, it's going to throw an error because it
Yeah.
doesn't know what that variable type is. And I could try changing that to character, which is another. Well, character
Well,
is a
you gotta highlight.
with a. Let's see. Cannot initialize a variable of type character with an I value of type constant dot vex dot direction type. So so this is going beyond my knowledge of C. Is but there's got to be a way to do it. But maybe character is not the right way to store it. I wish I could get a little more. So, but because that direction type, since it is a constant that Vex uses, so that's why it kind of highlights orange. But there's got to be a way to store that constant some way. But that's not something I want to bog the class down with. So that's going to be my own independent research here. So we'll worry about that kind of stuff later.
Don't you normally do the double and sign whenever you are going through? with your stuff? Like you put the and sign and then followed up with another and sign in that?
If you're well, the
Yeah,
double
so
and
like
sign.
this, yeah, like right there. So whenever I was doing it in my code, I was noticing that one of them would pop up and it would give me a yellow warning.
If you just do one and sign.
No, I did two like that, but
Uh-huh.
it would give me a yellow warning and it would tell me something along the lines of, what did it say? It's like it's not being noticed or something like that, or it's not doing anything. But
Hmm.
it didn't affect the code itself. Like it didn't make it where I couldn't use it. It gave
Yeah,
me this yellow warning and said that it was like what it asked me the question basically, what was the purpose of this?
yeah. Yeah, the yellow yeah, the yellows are just warnings. You oftentimes get them, for instance, like if I declare a variable that I'm not using, sometimes you'll get that warning. Let's see if I get one now. No, I didn't get it this time. But yeah, oftentimes you'll get it when you declare something that you're not using. But let's not, like I said, let's not bog ourselves down with that. Because I mean, it's already confusing enough for you guys without watching me get confused and struggle with it. uh, so so let's just kind of maybe stay in our lane for now, and then we'll kind of look at it later. But speaking of staying in our lane, yesterday I didn't really get a chance to show you how we could do proportional control. And I would really, really, really like us to do that, just because I want, and you may decide not to introduce it to your kids, but PID or PID control, uh, which proportional is probably the biggest component of that, um, is used everywhere in robotics and industry. Like your thermostat runs off of PID control. Your refrigerator, I don't know. There's so many things. Like um, anytime that you want to just kind of auto adjust things, um, then PID control comes up. So, like for instance, in the case of your thermostat, um, let's if you're really far away from your target temperature, it might run the AC like really really hard. Um, versus like if you're kind of close to the target temperature and maybe not run it as much. That's kind of what's going on there. And there's a lot of things too. So when we talk about PID or PID, that stands for proportional, integral, and derivative. I'll stop my share for a second. And those are just kind of. eh, when's the last time you guys have had a calculus class?
20 years ago.
Yes, probably so. If you've taken calculus at all,
Never.
I mean, yeah. Um, however,
I
um,
only made it to Calc 2.
it is something that you kind of look at in physics too. So, as well, Josh,
Yeah, I had to teach myself a little bit of calculus just for some physics stuff, but mine is algebra based, so it's not as big of a deal.
yeah, because the calculus and physics go hand in hand because they were both invented at the same time by the same person to complement each other. Um, but basically, uh, okay, so let's say we had a if we had like a graph, like an XY graph, and we had a curve on it, right? Um, the the proportional part is how far that curve is maybe like away from the zero on the plane. So the closer if the zero on our plane is our target value that we're trying to get to, then that curve, wherever the curve is, how far away that curve is from the zero at any point along that curve, that would be like that could be our proportional part of our graph. Um, and pictures would probably be better. Let me just draw something. Okay, so let's say we had a graph and then we had some curve on it. So I'm just gonna make it. So like let's say we just had a graph and we had some kind of curve on the graph. How far away it is from, and it wouldn't necessarily have to be a 0, but well, whatever your target value is, that would be your proportion. And so the further away you are, the bigger that proportion is. Okay, so that's the proportional part of PID. That's how far away you are. The integral part, an integral is just the area under a curve. So so like if you were to kind of like from where we started, what that area is, you could kind of like calculate that area by and with calculus it's pretty easy to calculate that area. But let's say if you're consistently above the curve, then that area is going to always get larger and larger and larger. But if your curve actually went below the 0, then sometimes you would have negative area, and that total area would kind of subtract from each other. And then the derivative part of it is just the slope of the line at any given point. So if the line is if the curve is horizontal at that point, the slope is 0. If the curve is more vertical, right, then that slope would be like 1. Or kind of like anywhere in between, and it could be like a negative slope or a positive slope, but wherever the slope is on that curve. And in real life, what you might have is you might be constantly adjusting something to say kind of keep it at a target position. And so it might start off like way above that target position. And then you're adjusting things, and then you might overshoot it and you might be below the target position. And then you might go back and overshoot in the other direction. But you're trying to adjust your curve so it, like, say, matches that line. And that's kind of what this PID control is all about. It's trying to adjust your curve to meet your target, whatever it is. And so by adjusting a correction based off of where it is, how far away it is from where it should be, that's the proportion part. But if you're constantly like above your target or constantly below your target, that's where the integral will kind of kick in. Because if you're constantly above the target, that area under that curve is going to get bigger and bigger and bigger. And that means that you're probably not correcting enough. And so you need to like kind of feed in another correction based off that integral to make sure that you're reaching the target. And then finally, the derivative part, if your slope is getting like really big, that means you're having these really big changes. And so if those changes are just being too drastic, you can kind of do another correction of the derivative to kind of like mellow out so that the derivative isn't so big, so the slopes aren't so big. But the biggest impact that you can have is probably the proportional, and the other ones only, like the integral and derivative, you can kind of ignore a lot, especially like the derivative, unless you're really trying to kind of like smooth out your curve a lot. Integral really doesn't come in unless it's a situation like a situation like, say, maintaining your arm. Because when you're maintaining like an arm, like lifting up, what can happen is gravity is going to pull it down, and so you're almost constantly under that target value. And so if you're consistently under that target value, then that integral could kind of kick in to help add some more power to keep it up. But in most cases, like us trying to hold our position, we're just kind of or trying to keep two things going, we're probably more concerned about that proportion. So
Would that
the
be
P part.
because as you adjust the proportion closest to the target value, the derivative basically would become the slope of that line of the target?
Yeah.
So
Yeah.
changing one changes the other essentially. Like if you adjust the proportionality, then that's going to affect the derivative.
Yes. That's also true. So though it's hard to it's hard to really explain this a lot without getting too deep into like the calculus portion. But basically what doing a correction to the derivative part of it can do is it can it basically smooths out any drastic changes. Is basically what adjusting the derivative does. But what we're going to do is we're going to write a program, and we're going to just worry about the proportional part of a PID. And so we're basically just going to write a P loop, not a full PID loop, not a full PID, but a P loop. And basically what we're going to be doing is we're going to be comparing the left side and the right side. And the bigger the difference in those two sides, the bigger the correction we want to make. So for instance, if the left and right sides are the same, then the difference will be 0, and then we won't make any correction. But if the difference is like a really big number, then that means we're going to do a really big correction. And so the bigger the difference, the bigger the correction. And so that's a little different from what we were doing yesterday, because yesterday it was just like, if there's any difference at all, we're going to do this correction or this correction. And if there's no difference at all, we won't do a correction. Because that's basically what we're doing. Where it's like, if there's if left is greater, then we're going to just slow down left by a fixed amount. Or if right is greater, then we're just slowing down right by a fixed amount. But we don't really have any, it's not taking account how big the difference is. So even if there's like a little tiny bit difference, it's still doing that set constant correction, which is probably overkill, which is why oftentimes you might get kind of a squiggly kind of path when it's driving. So let me show you. Let's write a code for that. And what I think what you guys are going to find is this is actually, the code itself is actually much simpler than doing all those if statements. So let's just do a new, and this isn't an actual assignment here, but let's do a new text project. I'm going to call it like Eric Smooth Straight, maybe Smooth Straight. And let's I guess I can name it, and yeah, let's follow all our, so let's and today is the 12th, 6 12 25. And we'll call this, I don't know, a smooth auto straight with P control. And we're gonna go ahead and set our motors. So we'll continue to have a left motor and a right motor. And I'm gonna reverse my left motor. and keep my right motor normal. My right motor is in port 10. And that's going to be normal. Okay, so let's kind of write some code here. Let's just make our robot just go straight forever until we pick it up and stop it, or until the battery goes dead. Or, well, how about let's make it go forward until a bumper is hit. So, because like because we're going to be adding bumpers to our robots later, anyways. So, and we're going to be introducing that. So let's add a bumper here. So if we go to add device, you might notice that at first you don't see bumpers at all on here. And that's because those bumpers are 3-wire devices, and they're going to plug into the lettered ports. So that's what we're going to pick here. We're going to pick 3-wire, and then we have all our different things like limit switches and bumpers. My bumper is plugged into port A. So I'm going to pick this bumper here, and it's going to be in port A. And honestly, I'm kind of fine with that name, just calling it bumper A. Now, even if you don't have a bumper plugged into your robot physically, you could go ahead and add it here so that later on you can do stuff with it. So basically what we're going to do is we're going to write a while loop, and it's going to run as long as the bumper is not being pressed. And then once it is pressed, we're just going to stop the robot. So we can kind of say that goes forward until the bumper is pressed. So we're gonna say while, and then we want a condition inside this while loop. And what we can do, we can just go into sensing if we want to. And since we added that bumper, we have this sensing, this bumper pressing. So we can drag that in. Now, this is basically saying that while the bumper is being pressed, we'll do something inside the loop. But however, we kind of want the opposite of that. We want while the bumper is not being pressed, we want to do stuff. So what we're going to do is in front of this pressing here, well, there's a couple of ways we can do it. We could say while it's not equal to true, or we can just put a not symbol in front of this. So a not symbol is just an exclamation point. And this basically means, instead of meaning while the bumper is being pressed, now this means while the bumper is not being pressed. We're going to do everything inside this loop. And then once we kick out of the loop, we want to stop our motor. So we'll go ahead and put our left motor dot stop and our right motor dot stop. And we're doing that outside of the curly brace for the while loop. So after we kick out of this while loop, we'll stop the motors. And I know you guys are kind of writing and typing along at the same time. So if I get too far ahead, please tell me to stop or slow down. But this is what we have so far. we created a left motor, right motor, and a bumper. And while the bumper is not being pressed, we're going to do some stuff, and then we're going to stop. Once the bumper is pressed, we're going to stop. Okay. Now let's focus on our code inside the loop. So what we want to do is not only do we want to go forward, but we want to go forward with checking our left and right sides and making sure they're the same and kind of controlling that. So we are going to go ahead and set up some variables. And we're going to do our variables outside the int main. So let's declare some variables. One thing that would probably be, well, you don't have to declare target speed, but let's declare a speed, so that we can control how fast we're going. So I'm going to make it we're going to let's work with voltages. And I'm going to make it a float because I kind of want like decimal points in my voltages. And we'll just call this variable speed. And that's going to be like the average speed that the motor is going to be going. But they're going to be adjusting their speed, but they're going to be kind of staying around this speed. And let's say 6 for 6 volts because I want to use voltages because I said before, like if we're using just the speed, like the actual speeds, like if we're adjusting the speed by percent or by RPM, then that command is actually doing a lot of the adjustment work for us, and we kind of want to do that and just work on our own. Now, anytime you're using like a P loop or a PI loop or a PD loop or a PID loop, and anytime you're using any of those controls, you typically have, well, anytime you're using P control, you're going to have 2 variables, and one of them is called error, and we're going to make that error a float. And we're going to start off setting our error to 0. We're not going to have any error at all. But that error is going to keep track of the difference between the two, between our left motor and our right motor. And then we also have a variable. It's also going to be a float, and we're going to call it KP. And we'll have to kind of like look at what we could set KP to. Let's just set it to 1 for now. What KP, oftentimes when you use a lowercase k, that means a constant, and that P just stands for proportional. So we're creating this proportional constant. And basically, that's going to affect how big a difference this proportional will have. It's basically a multiplier is what it is. So the bigger this KP is, the bigger you're having a proportion have an effect on your error. And in fact, I think 1 is probably way, way, way too high. So if your KP is like really, really high, that means that it's going to be adjusting a whole lot more. And so you might have like bigger, more dramatic turns as it's trying to adjust as you make your KP higher. But if your KP is lower, then it will have smaller adjustments. But if your KP is too low, those small adjustments it makes might not be enough adjustments to fix the problem. So there's a bit of tweaking with that KP value so that you have a sweet spot. So it's not like adjusting too much where it's just wildly swinging around, but it's also adjusting with enough swing to correct any problems that it's having. Any questions so far?
I don't.
Okay. Okay. So, inside this loop, we're going to be doing a couple of things. The first thing we want to do is calculate what our error is. So we're not going to declare error again, but we're going to set a new value to error. So we're going to since we're not declaring it and we're only like updating it, we don't have to say like float again, because we only say the variable type when we're declaring it. But what I'm just going to say is error, and then I'm going to assign a new value to error. And so in this case, the error is just going to be the difference between the two motor positions. And so what I'm going to do, and I'm not going to use the absolute value for this, but what I'm going to do is I'm just going to grab the and this can be found under sensing, but I'm going to grab the left motor position in degrees, and I'm just going to subtract the right motor position in degrees. And I'm not going to do the absolute value here because I do actually want to have a positive or a negative error. Sometimes I don't want a negative error. So if we think this through, and let's build. We haven't built in a while. Okay, no errors so far. So for instance, if both the left motor position and the right motor position, if they're both at 100, then the error is going to be 0, because 100 minus 100 is 0. If the left motor is at, like, say 100, but the right motor is only at 90, then my error is going to be 10, because it'll be 100 minus 90. Or if my left motor is at 90, but my right motor is at 100, then my error is going to be negative 10. And like if my left motor is at, say, 200, while my right motor is only at 100, then my error is going to be like 100. And so as we can see here, the bigger the difference between the two, the bigger that error is going to be. So are we good with that so far?
Yep.
Okay. And we only have 2 more lines of code to write, and we'll be done with this, believe it or not. And so now that I have this error calculated, now I want to go ahead and actually run my motors. So I'm going to use that motor spin. So I'll say left motor dot spin. We'll say forward. We are going to say how far we're going to go, or how fast we're going to go. Well, we're going to use voltage. So that's going to be speed, and which in this case is 6 volts. So that should be about half speed. But now what we're going to do is it's either going to be plus or minus. We'll write plus for now, but we'll kind of work through that and see if that's right. Plus our KP. So that's how a big an effect the error will have times the error, and that's going to be in volts, or volt, just volt. I guess I can put spaces here to make it prettier. So that KP is way too high. Now I'm looking at it. Now, I said before, I'm not sure if this should be plus or minus. And to kind of figure that out, let's walk through some situations. If the left motor gets ahead, we actually want to slow down the left motor, don't we? Isn't that always been the kind of case?
Yes.
Okay. So, honestly, we might need to subtract. So let's do some situations. So let's say left motor is 100 and right motor is 90. In that case, the left motor is ahead, and my error is going to be 10, right? That KP is way too high. Let's maybe set this instead of 1. Let's set it to 0.1. So let's walk through that situation. So in this case, my error is 10 because my left motor is ahead of my right motor. And so my speed is going to be 6 plus 0.1 times 10, which would be 1, so 7. So that's actually speeding up my left motor. And we wanted to slow down the left motor. So what I'll instead do is I'm going to subtract that KP minus error, times error. So now, if we go through this situation where the left motor is ahead, and let's say it's 10, the error is 10. Now my speed's going to be 6 minus 0.1 times 10, which is 1. So 6 minus 1. Now my speed's going to be 5. So, and that's kind of what we want because we want to slow down that left motor. So it's slower than our target speed. And then we'll do our right motor. Spin, forward. And with our right motor, we're going to do the opposite. We're going to add.
Wait, Eric, one sec. Can you go back to the math on that? Because I'm getting something totally different.
Okay.
So the speed is 6, right?
Okay, yeah.
And then we're subtracting 0.1 from that.
0.1 times 10.
Oh, okay. So wait, so you do the constant times the error first and then subtract it out.
Yeah, because that's your order of operations, right? Remember PIMDIS?
Yeah, you're right. I'm used to seeing things with parentheses.
We can put in parentheses if that
No, I'm good now. I'm good.
Yeah. I mean, if it's easier to see that way, you can put the parentheses in. But order of operations is going to do the multiplication for us before it does adding or subtracting. So okay, so and then we're going to do plus the KP times error here. Because once again, if my error was 10, with my left motor being ahead, now my right motor speed is going to be 6 plus 0.1 times 10, which is 1. So that would make my right motor speed 7. And so my left motor speed is 5 and my right motor speed is 7, which is kind of what I want because I want to because if my left motor is ahead, I want to slow down the left motor and speed up the right motor. And then we can also maybe let's go through the situation where the right motor is ahead. Let's say the left motor was at 90 and the right motor was at 100. Then my error is going to be -1. So negative 10. It would be my error, -10. And so then I would have for the left motor speed, it would be 0.1 times -10, which would be -1. So we'd have 6 minus a -1, which would be the same as 6 plus 1. And so in this case, my left motor speed would be 7. And then my right motor speed would be plus a -1. So our right motor speed would be 5, which is what we want, because if the right motor got ahead, then we want the left motor to slow down and the right motor's, I'm sorry, I got that backwards. The right motor speed, left motor speed up and right motor slow down. And as we can see here, the bigger the error is, the bigger the difference, the bigger the effect this is going to have on the speed.
So for a competition robot, if we use something like this, we wouldn't use voltage probably. We would probably use speed like we did earlier in the class. That way it
Yeah.
could become even more accurate.
Well, in some ways, you might be better off using the voltage. Even with a competition rope, because the reason being is because you don't have, because literally when you're using like a set velocity, or when you're saying a motor spin with a velocity, it's actually doing its own PID loop inside. So it's doing this as well. So you're kind of like doing it twice. And while you have control over your own PID loop, where you can kind of set the constants, you can't affect the constants inside the PID loop of like the motor spin, because those are kind of hard coded in. And so, so it's like you're trying to readjust something that's already being adjusted. Whereas if you just work with the voltages, then you're adjusting that raw output. So if you're trying to adjust the velocity and using the velocities to start with, you might because it's going to be trying to fix stuff while you're fixing stuff, and it's doing it about at the same time. So while you're doing it, it's doing it too, and so you can end up with kind of some erratic behavior. Does that make sense?
Yes.
Okay, so notice this built, okay, and notice this loop is much smaller than the loop we wrote before. Because that loop we wrote before, we had do this stuff if this is greater than this one. Else do this stuff if this is greater than this. Else then do this thing. So we had all the stuff that going on. In this case, all we're doing in this loop is we're figuring out the error, and then we're adjusting our speed based off that error. And then we're just kind of doing that in a loop. So as you can see, it's much less code to write. And this does a better job of correcting too, because once again, it's correcting in proportion to the rest of it. By the way, do you guys mind if I take a short break? Can we take a 5-minute break?
Sure.
Yep.
Okay.
Sure.
All right. Let's take a 5-minute break. Maybe you guys can just.
I think you muted yourself.
Oh, so you guys can kind of just discuss amongst yourselves while we take this break if you want. Maybe you could say, man, that guy's crazy. Why are we doing all this? Or maybe this isn't so bad. Whatever your opinions are.
So yesterday we just did the one project, or is there more that I'll need to catch up on?
We wrote 2 codes. I can show them to you. I don't know if I'm allowed to screen share at the same time as him. We did like both the unit 8 activities, activity 1 and activity 2. We did activity 1 together, and then he let us do activity 2 on our own.
Okay. And then Tuesday with the group meeting, was there content in it or was it more just informational?
No, we just introduced ourselves the whole time, and then the newbies kind of said like, what are we worried about? And then the people who've been teaching for a while gave us advice.
Okay.
All right, let's see if I can share. Can you see the code, the go forward 15 feet?
Yeah, I'm going to see if it, I'm zooming from my phone and working from my computer.
Okay.
Okay. I think I got it. Thank you.
No problem.
I did find that we have to make a 70% on this test on Tuesday. Just hoping I can pass it. I'm nervous about that. I'm gonna be honest.
I made a Quizlet for like all the like the definitions and words and stuff from the homework because I'm nervous too.
Yeah.
I
I've
can
started
share
on.
that.
Okay. Yeah, I started on 1 too. I haven't finished it, but
All right, did you guys finish bad mouthing yet, or?
I don't know. This is much easier than yesterday, so
Yeah, it is. It's easier and it does a better job of doing the stuff. But as I was saying yesterday, one of the purposes of us doing our autocorrecting like we were doing is because we were trying to introduce if statements and while loops. And so kind of the goal of it was to do something with if statements and do something with while loops. So that's kind of why we did it that way. I saw Ashley had her code up. Was were you having problems with the code, or were you just showing it off, or?
No, Lisa asked what we did yesterday, so I was just showing her this one.
Yeah, it was kind of complicated, right? That was probably our most complicated one yet.
I feel like yesterday you showed us kinematics and forces, and then now you're showing us energy momentum, and everybody's like, "Really? That's all we had to do?"
Yeah, I guess so. Yep. Yeah, that is true. If you just look at it from a different perspective, the math gets a lot easier. Before we move off of the PID, or just a proportional control, if we had wanted to do the integral and the derivative, basically, just like you have a KP, you could also do a KI for the integral, and that way you can adjust the weight of the integral, and do a KTD for the derivative, and so you could adjust the weight of the derivative. And basically, what the integral is you just want to keep up with the total error as it's going. And so you can make another variable called like something like total error. And every time you go through the loop, you could say something like total error is equal to total error plus error. Well, when I say equal to it, once again, that's an assignment operator. And that would kind of keep, every time it goes through the loop, it's going to be adding the error to the total error. And so it'll kind of be keeping up with a running total of the error as the program runs. And then just like how we have like we're adding, subtracting by KP times error, we could also out here, we could add or subtract by the KI times the total error. And that would be it for the integral part. So it's pretty much like, it's very similar to doing like the proportional. But that total error will only kick in if you're consistently either above or below every time. So if you're always above your target value every time, then that total error is going to add up. Or if you're constantly below the target every time, then the total error is also going to add up. It's going to be adding up with a negative number. However, if you're always around the target value, like maybe sometimes above and sometimes below, well, the times you're below it are going to subtract out from the total error. Well, the times you're above it are going to add to the total error. And so if you're constantly like just above or below it, that total error is going to be about 0. And so what's going to happen is that integral portion that will affect your speed, that really only kicks in if your total error gets too high or too low. But if it's constantly like around that value, like if you were doing a graph of this, if you were plotting like your error versus time while you're doing and correcting, oftentimes what will happen is like it will kind of fluctuate between that total value, between that target value. And then that's where the derivative will kick in. The derivative, if you're fluctuating a lot, that derivative can help smooth out that fluctuation a bit. And the way you do that for the derivative, instead of keeping up with a total, what you want to do is you want to compare your current error to your previous error. So you would probably create another variable called like last error or something like that. And then like at the end of the loop, after you run through the loop, you would like store that whatever your current error is into last error. And then the difference between your current error in this loop and your last error from the last loop, that would be kind of like your derivative there, because basically, basically you're kind of slicing up that graph into time slices where every time you go through the loop is another slice of time. And so the difference between the area from the previous slice and the current slice, that is actually going to be your slope of your line there. Because that's, once you into those tiny slices, that's kind of what your slope is. It's going to be the difference in height between the last tiny slice and the next tiny slice. And so you can also, just like with adding plus or minus the kp times error, then you can do adding the kp or the kd of the difference between the error and the last error. But that being said, you don't necessarily need to do the I and the D. KP will do the bulk of the work for you. So just doing the proportional loop will do like 99% of what you're trying to do. It's just like, if you want it even better, then you can start working in the Ki and the Kd, or the integral and the derivative to have an even better, smoother turn. But the bulk of the work is going to be done by the proportional. And so if all they learn is the proportional, that will get them most of what they need. And we wouldn't necessarily want to confuse them like I'm confusing you right now by even talking about even more stuff.
It worked pretty well, by the way.
Yeah, I bet it did.
Are you reading it, Josh?
Yeah, and it was noticeable. Like you could actually see the little corrections, and they were just micro corrections, and it stayed straight, as opposed to like yesterday's. Whenever it corrected, it would not necessarily go back to what the original straight was. It would be kind of off. And so, like whenever mine finished, it finished basically in the same spot, but it was tilted a little bit from what its original position was. And so this, I mean, it's not, it's a lot closer to, I also wasn't doing forward and back. I just did the forward part, but it held a pretty straight arrow at least.
That's cool.
Yeah. And so, and once again, it's optional if you want to show the kids this, but it's just such a, it's such a useful thing, and it is used in the industry so much, and it does such a much better job of it, and it's also simpler to do. So I think there's a lot of benefit for showing the kids how to do at least proportional control.
Now, how much battery life does this take relative to what we were doing yesterday?
I would say it would probably be close to about the same, or maybe slightly less, because actually it is going to be less, because all you're doing is one calculation, and then you're setting the speeds. Whereas in the other case, you're doing a lot of you're doing at least one comparison, but probably on average, probably at least two comparisons every time you're going through the loop.
It seems like this is much less processing power.
Mm-hmm. Yes. Because you're only doing that one calculation every time you go through the loop. So so it's even more efficient too. So just so many benefits there. Yep. Okay. So so now that I've kind of ranted about that, let's actually look at Unit 9. So Unit 9 has two parts to it. I'll share my screen. The first part is about functions, and the second part is about the bumper sensor. I think this first part also talks about conveyors a bit. And I think that was mostly throwing it in there just because we've been doing so much programming in the last few units that they probably wanted to add at least some building. I'm going to go ahead and load up both sets of slides. It's so fast, this computer. Dun, dun, dun. So functions are what we're talking about today, and functions are awesome. We have actually been using functions this whole time because every time we say something like motor spin or motor stop or like any of those, the spin for, those are all functions. But those are functions that have already been created, and we're going to learn to make our own functions. Because wouldn't it be great if instead of having to copy and paste all that auto straightening code every time, if we just created a function that did it for us, and then we just called on that function later. So when we got to like our int main, it was really just as simple as just calling on our function and maybe saying a certain amount of time or a certain distance we're trying to go and having it all done in our function for us. That would be cool. And that's what we're going to be doing. So functions, and they're so useful that it's kind of a shame that we don't introduce them earlier than this. Because they're kind of one of the more useful things you get out of programming. Yep. What are our learning objectives this time? So we are going to describe the purpose and benefits of a function, the advantages of a function, how to pass values to a function, and then we're going to do like an auto straightening, and we're going to redo our basketball drill using functions. And so instead of like writing all that code from scratch, we're going to actually probably just go to our auto straightening and maybe copy some chunks or a chunk out of our basketball drill code from yesterday. I don't actually have the basketball drill, but I have yesterday's code, so I'll pull that up. Or we have this nice smooth. Maybe we can use the smooth stuff for auto straightening.
Should we use the PID we just created for that?
No, I think that's perfectly fine. We can use
Cool.
that PID we just create. Yeah. Yep. So we can do that. Okay, so what is a function? A function is a portion of code within a larger program that performs a specific task and is relatively independent of the remaining code. So, and anytime you have a function, it's basically two things you got to do. First, you got to create the function. So in this case, we're creating a function called movement. And that's what we're kind of doing here. So we're saying, so void is a variable type. Just like how like integer is like whole numbers and float is like decimal numbers and char is like a single characters. What void is a variable type that is nothing. Void just doesn't store anything and so when we declare a function, we need to kind of say what kind of values are being returned, like what we're supposed to get out of that function. So honestly, like when we have int main, it is actually once main is done, it actually returns a value. Usually, I think it returns a 0 when it's done. But if we're not returning anything, then we're just going to say void, and void just means that it's not going to have anything. So it's not going to return any sort of information when we're done. That's basically what that is. So we declare a function pretty much just like we do with a variable. So we say what type it is, and we doesn't have to be void, by the way. So for instance, if we're doing a calculation in here where we may be adding two numbers together, then we could return the value of that. And if it was like, say, an integer that we're trying to return, then we could say integer here, int. But in this case, all we're doing is moving these motors, And so we're not really returning any information. So we're just going to leave it as a void. And in most cases, the functions we write for our robots are going to be voids. But if you're trying to do other things, you might return something else. So that's what that void means. And then we have the name of the function. And where it's a little different from declaring a variable is that we do need to put these parentheses here. And if we had any kind of parameters we were trying to feed into the function, that's where we put our parameters in. And we'll actually do that later. And then just kind of like how we did with loops and our if statements, we are going to open up a curly brace, and then we're going to put any code we're doing inside that between the curly braces. And so basically, we're creating this function called movement. We're not feeding it anything, so we don't need to give it any parameters. And then basically, we're saying that anytime we say movement, we're going to do all these things. We're going to set our velocities to 100, and then we're going to spin our motors for 3 turns. And so once you've created the function, and notice that we do this outside the int main and above the int main, just like how we would with variables. Typically, most times you're going to create, you'll probably have your variables first, then any functions that you have, and then your int main. Because typically any variables you declare, anything that's going to be used, like if I made some variables to use in this function, those variables need to be above the function. So that's why typically you put all your variables first, then you put all your functions, because those functions might be used by the int main. And then you can have your int main. And in this case, so we made this function called movement, and then in our main, now we're calling on that function. And so, and I'm just calling it by just saying movement. I still have to do the parentheses. And then if I had parameters to feed in, I would feed in those parameters. But in this case, it didn't have any. So I just say movement, semicolon. And now when I run int main, it's going to run movement. It's going to say, oh, well, I got this function movement here. Well, what's movement? Movement's doing all this stuff. So every time I call a movement, it's going to do all this stuff. And so, for instance, if I said movement, semicolon, and then another movement, then it's going to go 3 turns for movement, and then it's going to go 3 turns again for the second movement. So every time I call a movement after that, it's going to be doing this stuff. So if you have some situation where you're doing things multiple times, then that's a situation where it's really nice to have a function. Like in the case of our basketball drills, wouldn't it be great if we just had a going forward function and then a going backwards function? So I could just say like go forward and maybe even feed a parameter. Like if I said go forward 2, it would go forward 2 feet. And then if I said go back 2, it would go back 2 feet. And then I could just say go forward 2, go back 2, go forward 4, go back 4. For my and so in that case, I would only need these 2 functions. I could just have a go forward function and a go back function. And then I could just call on those functions multiple times. So as you can see, that would cut down tremendously on what we do with our basketball drill.
So in the case of like the basketball drill, right? So like if you're using, because I'm assuming you can't, or can you call the variables, like if you're calling on different variables in that function, then you'd have to write it, like would you have to, like if you were doing the 4 feet, would you have to like say do that function times 2 to get it to, I'm trying to figure out how do you like change it, like make the function useful for like different movements, like
Okay.
2 versus 4 versus 6 versus 8.
Okay, yeah. So one option is you could just call on that. You could just call on that go forward 2 times to go 4 feet. But another option is that's where parameters come in. And we will, in a couple of slides down the road, we're going to introduce parameters. But basically, Do you know how like say when we use spin for or just spin, how inside the parentheses we say some different things? So like for instance, with our spin, we can say spin forward 50%. And so we're changing what that spin does depending on what parameters we feed in. In the same way, we can write when we write our functions, we can specify parameters to use so that we can say. So, for instance, I could say maybe I have a parameter up here for distance, and then I can feed in say a 2, and if it sees that 2 there, it's going to go, okay, well that 2 matches. That's going to be fed into distance, and then anywhere I use distance inside, it's going to take that 2 and kind of feed it along. So we can that's called like passing a parameter. And that's actually where the real versatility of functions come in, is when you can actually feed parameters in that function. So that one function can do a variety of things depending on what parameters you feed to it. So yeah, so that's where that's going to come in. Yep. Okay, so basically what's going on here is that when I call on a function, it's going to go, oh, okay, so I'm calling on movement. What is movement? Well, movement is doing a turning the left and right motors 3 times at 100% speed. So I'm going to do that. So when I call on the function, it's going to go and look up the function and then do everything that's in that function. And then once that function ends, then it's going to go back and continue on with the main part of the code. And so I could call on that function over and over and over again if I wanted to. So what are the advantages of functions? Well, as it says here, they allow you to reuse code rather than retyping groups of commands. And they allow you to group a series of steps under one name. They save a lot of time and space. And they make your code easier to read and understand. All big advantages. Yep. So parts of the function. So you declare a function above the int main. And just like a variable, you do have to declare what type of information you're feeding back. But oftentimes, with the functions we're writing, we're not sending anything back. And so we usually will say void. Then we have to have a name for the function. And the name of your function follows the same rules as your names for your variables. Like you can't start with a number. You can't have any spaces in it. You can't have any special characters other than underscore. So the same rules apply to name functions as they do with the variables. And then and then you do need your parentheses. And then if you had parameters, you would put them in the parentheses. And then finally, you would open up a curly brace, and then you would put all you're trying to do in that function in between the curly braces. So you're defining what your function does. So in the similar way, like when we declare a variable and we store information in the variable, the curly braces is what you put in between the curly braces is what you're kind of storing in to what you're doing in the function. I like to relate to it as like if variables are nouns, and functions are kind of like verbs, because variables you're kind of storing like things, like numbers and stuff like that, but those things aren't really doing anything. While with functions, you're kind of storing verbs. You're storing things that you're doing. Like when I call in this function, I'm doing all this stuff. And then so after you've declared a function, then in your main code is where you call in the function. And by the way, you do not. You could have functions that call on other functions. And you can have functions that call on functions that call on functions. But if you do that, it's really, really important you have the order of the functions right, because you can't call on a function before it's been declared. Um, so so if you have a function that calls on a function, like for instance, one thing, so we might have a function for going forward, right? But we might write another function for printing stuff to the brain, and maybe we don't want to type in like uh, all the stuff that we type in every time when we print stuff to the brain. Maybe we want to just write a function for that, and then just call on like a print screen function, but that also does like print screen and new line and maybe adjust the color and the all. We could put all that together in a function, and then we could just call on that every time we wanted to put some stuff on the screen. And and then we could call on that inside of function for moving forward, so that every time we're moving forward, we're the first thing we're doing is calling on this function where we're doing all this printing stuff. And so, but um, but once again, you can, since int main is a function too, you basically you can call on other functions inside that int main. Any questions so far? Okay, great. So let's say if we had this code right here. Once again, this is that same movement function we looked at before. So every time I call on movement, it's just turning 3 turns. So if I called on movement 3 times, it would do the first movement and work its do 3 turns, and then it would do the second movement, turn 3 turns, and the third movement, turn 3 turns. So we'd end up like doing a total of like 9 turns here when we do movement like this. And there are times where it's useful to just go fixed distances and do fixed turns. Like for instance, if you were trying to have the robot go through a maze, but that maze was kind of laid out in a grid pattern and all the grids were the same distances, then you can maybe have a forward that only goes forward like one grid or one block of that maze. And then maybe you have a turn left that turns exactly 90 degrees and a turn right that turns exactly 90 degrees right. And so you could have functions for that where they go like the blocks of the maze, and then that would kind of make sense because really all you're doing is you only are wanting like to go forward and say maybe 2-foot units or however big the maze blocks are. So this right here, we're creating a function and we're calling on it 3 times. This used up like 12 lines of code to write all this. However, in this case, we're doing the exact same thing because we're ultimately we're only moving forward 3 turns. Here, we're not declaring a function and doing all that stuff. We're just doing it, and we're just going ahead and moving 9 turns. And we able to pull that off with 6 lines of code. So sometimes functions aren't always the most efficient way to do things. Like if I'm only doing this once, I really don't necessarily have to write a function for it. I could have just done it like this. So there are times where it's not always the most efficient thing to make a function, code-wise. However, like so for instance, like what if we don't want to move 3 turns every time we call a movement? Or what if we don't always want to go 100% velocity every time? Well, that's where these parameters come in. So that's where we can pass variables through. So here is an example of a function using parameters here. So we're still declaring the function. And once again, this is a void. That means we're not sending anything back. But here, we're creating 3 parameters in here. And we create a parameter just like we create a variable, in that we need to say like what type of data this parameter is. And we also need to give that parameter a name. So this is saying that when I use movement, and I'm going to need to feed in 3 numbers into it. And all 3 of these numbers are going to be integers. And the first number I feed in is going to be assigned to turn distance. The second number that I feed in is going to be fed into a speed L for like maybe a left speed. And the third parameter I'm feeding in is going to be fed into a speed R. And so we're making those parameters, and we're going to, and so when I call on this later, I'm going to have to like say 3 numbers when I call on this. So like later on when I call on this, I'm going to have to say like movement, and I know my first is a turn distance. So if I want to go 3 turns, I would say like maybe 3. And maybe I want to go straight. So maybe I'll set my left speed and right speed to maybe 50%. So I'd say maybe 3, 50, 50. So if I said movement 3, 50, 50, then it's going to feed the 3 into the turn distance, the 50 into speed L, and the other 50 into speed R. And then inside our code here, inside our function, so I'm saying like left motor set velocity, and just how I would with a variable, I'm going to use that speed L, that parameter. So whatever I feed into speed L is going to be used for my set velocity here. So if I fed in 50, it's going to use 50 here. And same thing with my right motor. My right motor is going to speed R. And then my turn distances are going to be grabbed from here and fed in. So if I said 3, 50, 50, it's going to set 50 for this speed, 50 for this speed, and 3 for both of these turn distances. Now, honestly, this movement code is actually pretty versatile, because if you have independent control of both of the speeds, those speeds don't have to be the same. If they are the same and they're both positive, then I am going to go forward. If both of these are negative speeds, then I'll actually go backwards. And if one of these is a positive speed and the other is a negative speed, then I'll actually end up doing a point turn, because one will go backwards, one will go forward. So I can do a point turn to the left or the right by having positive and negative speeds here. Or if I want to do a swing turn, I could set one of these to 0 speed and the other one to like a positive speed. And then I could do swing turns. And then I can control how much those turns are, or how much I'm going forward or back based off these turn distances. So actually this movement code is actually really, really versatile, because I can go forward with it, I can go backwards with it, I can do point turns, I can do swing turns, and I can do all that stuff by merely just changing these 3 numbers. Any questions with what I've said so far? Okay, great. And so here, that previous function, we're calling on it. And so once again, notice I'm feeding 3 numbers into it. And so in this case, 300, 100 means that 3 is going to be my distance, and these hundreds are going to be my left and right motor speeds. Now, this particular function movement, I think, is going to show up in like the tests and stuff like that. So this example here will also show up on the quiz and also on the homework, I believe. For sure the quiz. So if you go and look at the quiz, you'll see like for like the debugging of the code, you might see this movement in here, or a function like it. And so once again, when I say movement 3, 100, 100, that 3 is going to go into turn distance because that's the first thing here and that's the first number here. And then that turn distance is later being used here and here. So that 3 is going to be passed into here, and that's going to be passed along here and here. And that 100 is going to be fed into speed L, and that's going to be fed over here. And this 100 is fed into speed R, and that means it's going to feed over here. So we're passing along those numbers through those parameters.
And
so
turn distance would be a variable that you will define prior to doing the.
No, so we're not defining it as a variable. It's a parameter. So this is actually, when we say int turn distance, that's kind of like declaring a variable, but that it only works inside this function.
So
you don't have to declare another turn distance like as a variable, because you're really declaring it here when you're establishing your parameters.
if we wanted to, like, let's say that we're doing the basketball drill, how could we make the turn distance 2 feet if we wanted it to be specifically 2 feet? Would we have to go through and do all the math, or would we be able to establish that without doing turns?
Well, do you remember? I think it was. Let me pull up the code we did yesterday.
I know that we did the code that we were able to solve for the number of degrees.
Yeah. Yeah, we could do the same thing with this if we wanted to.
So how would we get it to?
And we could do that calculation inside the function.
Okay.
I'm sorry, you cut out a little bit there, Josh.
Well, I was trying to figure out. So how would
say what we were saying one more time? What was your question?
How would we be able to get it to change without adding more variables, or would we have to actually add a variable to create what we're looking for as far as a turn distance?
So in this case, I would probably create another variable. Because what I could do is I could have a parameter for feet, and maybe I could just call that parameter feet. But then inside the function, I could do a calculation where I turn feet into the number of turns or the number of degrees, and I could store maybe that as a variable. Yeah. Or, I mean, you don't necessarily have, you don't actually have to clear you could do all the math when you're doing the spin, but that would just look messy, right? Because you could say like a left motor spin forward, and then you could do 12 times whatever, or I mean, you could do the whatever your feet was times 12. What was it? Divided by 4 divided by pi times 360, and you could do all that like right in there inside the spin if you wanted to, or the spin 4 in that case. But that would look pretty messy. So it's usually, if you're doing a lot of math, it's usually it's usually easier to read if you just make a variable to store all that math you're doing into, and then calling on that when you're done with the math.
And that's just like a preference. So like if I wanted to do like, like had the kids do like a tape for the basketball drill example. So if I wanted them to make like a table for each function call in. So like if they're doing the 2 foot, they're going to call these 3 values, and then they can just plug those in when they write the code.
Mm-hmm.
Does that make sense? I think that
what's the question?
No, I'm just like suggesting like whenever, like, since since you're
Oh, yeah.
calling three values, like if you're going to use the same function for like, for example, the basketball drill. So if you're having them do a function, you could
Mhm.
like have them make a table with the different movements and then the three values that they would plug into that movement function when they called it. So like if I was doing the go forward and I calculated the number of degrees for the distance, I'd have that number, the two velocities, and then I go to my next table, what I call the next movement in, I'm going to go plug in the next set of values.
Yeah. And you can
That just
make
may
like
make it easier for them. I mean, like I'm just kind of trying to think in the kids' logic. That may be an easy thing for them to do.
Mhm. And you can always make a glossary of your functions, right? Which is, I think, kind of what you're saying. Um, so, and also, typically, it's good practice that when you declare a function, then above it you comment like exactly what it's doing and what all the parameters are. So, like you describe what all these parameters are, and just have a good detailed description of your function. Um, and you probably want to put those comments with the function, um, so that you can kind of read it and understand what it's doing, what all these parameters I'm feeding into it are. Um, but it, or you can make kind of like what they did. So basically, in VEX code, basically we have kind of like a glossary. So we have all these functions here. That's what all these are on the side here. These are all functions, and then how we use these functions. Well, we can just click on any one of these help things to kind of get an explanation of the function and how it works and what we do with it. Um, so parts of the function. So what were we talking about? Okay, so like for instance, um, also it could be handy like out beside when you're calling on a function to maybe make a comment of your intended behavior for that function. Like so, like when I was saying movement 3, comma 100, comma 100 out beside it, I'm expecting it to move forward 3 turns at 100%. Or in this case, since I'm using -3 here, uh, 50 comma 50, it should be moving. Since it's a negative for the distance, a negative distance means it's going to go backwards. Or in this case, um, this has a negative speed. So if I'm going a positive distance, but with a negative speed, that's also going to go backwards. Uh, so so both of these are like two different ways that would do the same thing. They're both going to move backwards 3 turns at 50% power. Or in this case, with a negative, was the first parameter the left speed or the right speed? I don't quite remember. I'd have to go back and look at movement.
Left.
Yeah, the first one is the left speed. So if I have a negative left speed but a positive right speed, then yeah, that would turn left. Yep, like it says here. So it's going to do a point turn left for 5 turns. So um so if I was trying to do these things like go forward 3 turns at 100, move back 3 turns at 50, with this function here, this ended up being like 13 lines of code. Um, on the other hand, if I were to try to do the same thing without the functions, then that would be 19 lines of code. Technically, I guess we could shorten that a bit because actually these aren't equivalent to each other. Now that I'm looking at it. What's if these are supposed to be equivalent? What is the problem with this side? Can anyone point it out?
Would it be the second one? The right motor spin for, it says 3, but it should be -3?
That's it. Yeah.
Okay.
That's it. Very good. Raven's really nailing it today. Yep. Not re Yeah. Did I get the right person's name?
Yeah, that was me.
Yeah, okay, good. So I didn't have my I can't see who was talking. But yeah, you're exactly right because like if this is supposed to be the second, if this chunk of code is supposed to go with the second line, both of these should have been a -3. Yep. And technically, if if this was supposed to be a -3, that means this was backing up 3, and this was backing up another 3. We could have probably just combined these two and just said backup 6, right? And it would have done the same thing. So we could have cut that down. But yeah, that's definitely an error there. Once again, that is a picture. Well, we can just point that out. Maybe people won't even notice.
Well, the third set, they changed the speed to negative.
Yeah.
So that's right. Is that what they did differently?
Yeah.
Okay.
But going forward at negative speed is the same as going backward at a positive speed. So like these two, assuming that this was correct and you had a -3 here, these two blocks would do the exact same thing.
Right.
And so and so if the ultimate of these two blocks is just going backwards 6 anyways, and we could have just said spin for -6 and then just got rid of this block.
And then in the function, could you have just gotten rid of one of those lines and made
Yeah,
the
that's
six
true.
instead
Yeah,
of
that's
two?
also true too. I could have just got rid of one of these lines and I could have just said -6, 50/50. Yep. That's also true. So, yep. But in this case, since we're doing like a lot of different actions, now it definitely makes a lot of different things. It definitely makes sense to make it a function. Because, for instance, think back to our basketball code, especially the last one we did with all the auto straining in that basketball code. That was a lot of lines of code that we could have probably simplified down if we had simply had two functions, like maybe a go forward function and a go backwards function. Um, so we could have simplified that by a tremendous amount. And honestly, uh, what I was trying to do this morning that I was stuck on was I was trying to maybe instead of having a go forward and a go back, just a go that would do either direction. But I was having a lot of difficulty with the forward. That wasn't working out for me. So, so that was kind of annoying. Like I couldn't pass the word forward along as a parameter that it would accept, and I was still struggling to figure out how to do that. There's got to be a way to do it because it would be too useful to do not to be able to have a way to do it. Okay, so here is another function, and this would be a good function for instance, doing our if we were doing the Sentry bot. Because here we were moving straight for 50%, and then we're turning right for 3 turns. If that 3 turns happen to be a 90-degree turn, then this would be great for the Sentry bar because what we could do is we could go forward and turn, and forward and turn, and forward and turn. And so it could just go around and around and around our middle part for our Sentry bot. So to actually get those how far we need to go. That's where we could do some math and then also do some experimentation and tweaking to kind of tweak those numbers down to get them right. Um, but you
There's
could,
not a way for the motors to recognize a true 90-degree turn of the robot without sensors, correct?
that's right. That's right. And that's where sensors like the inertial sensor comes in handy because it's got that gyroscope, so it keeps up with orientation. And that's why you see a lot of competition robots use that inertial sensor because that sensor keeps up with your orientation. Um, and then what else? Or if you have the GPS sensor, it will read the barcode strip on the field to know its orientation. A lot of teams use odometry. Well, where what they'll do is they'll put tracking wheels on the bottom of their robot, and based off of the rotations of the tracking wheels, they kind of keep up with their position and their orientation with those tracking wheels. So, but yeah, so without sensors, it it's harder to because you can technically you could use the encoders as uh, encoders on your drive wheels as tracking wheels, I guess, and you could kind of use that if you had the correct math for it. Um, but you're gonna get a much more accurate thing if you use something like an inertial sensor to keep up with your heading. Um, Yep. Or you use rotation sensors and tracking wheels. So you can get a much more accurate heading that way. Uh, okay, so basically, we can use this as a turn, and once again, basically, we're taking that. Uh, Another thing we could do, as it's doing here, it's declaring a variable called dist for a distance. So it's assigning that to a variable, and they declared the variable inside it main, and you can do that. But it's just typically you would usually declare your variables outside of it main. But in this case, they did declare this variable called distance, and I think if we look at the slides, I think as a slideshow, yeah, it's this. Okay, so if if we declare this variable called distance, then we can feed in distance here as one of our parameters. That means it's going to go up here for our turn distance, and then we're going to use those turn distances there. Or in this case, distance times 2, that will be 10, which will feed 10 into turn distance this time, and then feed that along to our spin 4. Yeah, so that's parameters for us. Let me see if there's any code assignment for 9.1. Let me go back to 9.1. Did I save all the assignments for 9. Yeah, there is. Let's see what the 9.1 activity is. Oh, and it's 10 o'clock. So, and we just finished some slides. So this would be a good time for our break, right? So
Yep.
let's take a break and then we'll kind of look at the activity. Yep. So we'll take a 10-minute break and then we'll come back and we'll look at this activity 1 here. And the activity 1 is basically just doing a basketball drill, but with our function. Hey, everybody. Everyone have a good break? Great.
Got another cup of coffee, so we're doing all right.
Okay, so we've been introducing this introducing functions and their parameters. And so if we look at the activity we have for 9.1, it's basically doing our basketball drill with our auto straightening, but using functions this time. So just like before, it should go 2 feet forward, stop, travel 2 feet back, and then after it's come back, it should raise and lower the arm to shoot a basket. And we want to do this for 2 feet, 4 feet, 6 feet, 8 feet. So so overall, the code you have in your int main shouldn't really have that many lines of code. Like it says here, it should only have around 12 to 15 lines of code. In your int main, everything else should kind of be in your functions. So do we want to do that together, or do we want to? Do you guys just want to? Do that? All right, do it together. Okay.
You
The
ask like
first
you don't know
time.
the answer.
Okay. And then let me ask you this: do we want to do the auto straightening with our? Do we want to use our nice
Did.
new? Yes.
Yeah, I like the P
Yeah.
loop.
Okay. So let's maybe use our P loop stuff. In that case, would it be okay if we just edit this code?
I'm good with that.
Okay. So because everyone has this much of it written already, right? And so yeah, so let's just edit this code then. Does that sound good? Okay. Now we will definitely have to make some changes to code. For instance, right now this just goes forward until it hits a bumper. We're going to actually have to have it go forward for a certain amount of rotation or a certain on the encoder. So we'll have to change our conditions for our while loop and a few other things to really make this work. But let's save this as something else. So I'm going to change the name of this and save it as something else. Well, actually, I'll just manually save first to make sure this is saved. And this is probably going to be our last basketball drill. I don't think there's any other basketball drills after this one. So I'm going to say, I'm going to call it final drill. Well, I guess I should probably follow the conventions here. It's unit 9, I think. Unit 9, activity 1. I'll call it that. Okay. So we are going to want to keep these variables here. So we're going to leave those alone. After our variables, though, let's make a section for declaring functions. So I'm going to just say declare functions here. And we're going to make a function for so just to go forward. So we're going to make a go forward function. And then I think we're going to just need to make a separate function to go backwards. So we'll do that too. So let's make a go forward function. And we could call it something as simple as like go forward or something like that. So we're not going to return anything back. So the variable type for this function is going to be a void. And we're going to call it, I'm going to call mine go forward. And we do need to feed some parameters into it. And I think we only need to feed one parameter into it, just the distance that we want to go. And I'm gonna make it an integer and I'm going to call it feet because I really just want to be able to just feed in 2 feet, and maybe we can do all the math for converting that into degrees inside the function.
But
And then,
won't those answers not be whole numbers though? Most likely.
well, the feet will be a whole number because you're just going to say 2, 4, 6, or 8.
Okay, I got it.
The actual degrees we end up calculating won't be a whole number. And so that's our declaration of our function. We could go ahead and build this, and notice we don't have any errors. Now we just need to put our actual code inside of here. So let's actually just grab all our while loop stuff, and I'm actually going to cut it out. So I'm going to cut it out instead of copying it out. Control X. And let's just put it all up here. Now, what we kind of want to do, so we have this parameter feeding in called feet. And so like if I want to go 2 feet, then I should just be able to say go forward 2. Or if I want to go 4 feet, I should just be able to say go forward 4. But in order to go 2 feet, I actually do need to calculate how many degrees that's going to be. Now I can store that as a variable, and I could declare that variable up here and then update it here if I wanted to, or I could declare the variable inside the function if I wanted to. Now, in one case, if I declare the variable up here, that would be known as a global variable. And a global variable is a variable that everything can see. So main can see it, the go forward can see it. Everywhere, all throughout the code, it can see that variable. That's what it means to be a global variable. On the other hand, if I were to declare the variable inside the function, it would only be available to the function, but nowhere else could use it. In our case, it would be perfectly fine to make it and that's called a local variable. So that's also why, like, if we declare a variable in int main, we can't use that variable in another function. That's another reason why we typically declare variables outside int main. In our case, it's probably just fine to go ahead and declare it as a variable. But let's create a variable. We're going to make it a float, and this is going to be like the number of degrees that our feet are going to be. So I might just call it degs for degrees, and we can assign it whatever number we want right now. I'm going to start signing at 0 because we're actually going to update what that number is in our function. So we're going to make this variable called degs, and then let's actually assign a new number to degs. Let's actually do our calculations here. So I don't have to declare it. I'm just going to call on it. And now what I want to do with that is I want to take the feet, but then I want to do all the math to convert the feet to degrees. And from my earlier calculations that I have on paper, I know I have to multiply that feet by 12 to turn it into inches, and then divide it by 4, and also divide it by a pi to turn the inches into rotations, and then finally multiply by 360 to turn it into degrees. And so what that's going to do is it's going to take in whatever I have for feet. So if I had 2 feet, then it's going to do like 2 times 12 divided by 4 divided by 3.14 times 360. And that should tell me how many degrees I need to turn my motors. Now, if I wanted to, I did not necessarily need this variable as a global variable. I could have just declared it as a variable here and assigned it. Either way actually works. What are the advantages? Well, this local variable, if we do it this way, this variable only exists when the function is called on. And then it kind of goes away once the function's done. And then the next time you call on the function, it creates that variable again. So it's kind of like a temporary variable that's being created if I'm doing it inside the function. That can be, on the other hand, if I have it up here, and notice, by the way, if I build this right now, I'll probably get an error or at least a warning. Yeah, I'm getting a warning here because it's telling me that I've already well, it's saying unused. That's the warning. Okay, well, that's true. I figured I would get another warning saying that I've declared that same variable twice, but I guess not. So which way do we? Okay, so locally, it's only going to exist anytime you call on the function. It's going to create it, and then when it's done, that variable is going to go away. If I declare it globally, then it's going to store this value in here and keep it. It's going to just be there forever. But why would that be a disadvantage? If I forget to update that variable later, then it's going to use whatever the stored value is. So for instance, if I update it in my go forward, but when I later make it go backwards and I forget to update it, it's just going to use the old value that was stored. But for our purposes, let's just declare it as a global. We're updating it here. And now what we need to do is just change our condition for our while loop. So in this while loop here, instead of going until the bumper's not pressed, instead we want to go as long as the left motor and the right motor are less than degrees. And once again, let's go ahead and use our absolute values of that too. So what we're going to do is inside this while loop for our condition, we're going to say while the absolute value of the left motor position in degrees and we want 2 parentheses go outside 2 of the parentheses while that is less than our degrees, and the double and sign, the absolute value of our right motor. Let me minimize this so you can see it better because it's getting kind of long. Our right motor dot position. Why is that not lighting up? Maybe because I haven't finished typing it. Okay. Right motor position in degrees. And we want to go 2 parentheses is less than dex. Let's build this and make sure we don't have any errors. Because that was a long line of code to write, and it's easy to especially with the parentheses. It's easy to get errors with the parentheses there. I didn't get any build errors, but did everyone else? Was everyone else able to write that line of code out? Okay.
I have 2 errors, but it's on the left motor stop and right motor stop. So I'm trying to figure out what it's.
Hmm.
Did you add your motors?
If she's carrying over from the other code, and by the way, we don't need the bumper anymore. I guess we can delete that.
Yeah, I have my motors on there. Let's see. It says cannot use a dot on operator on the
do you have make sure you got your curly braces good. So for instance, there should be the curly braces for the while loop, and then the motor should be outside of that. But then you should also have your curly braces for your function, and those stops should be inside those curly braces.
Okay.
So they should be outside the ones for the loop, but inside the ones for the function.
Can I share my screen a second?
Yeah.
Okay.
Yeah, let me stop my share.
I'm sorry.
No, it's no problem at all. We're all here to learn together.
Okay. How do I make this bigger?
We have 5 errors. On line 90, click on the parentheses on line 90. Not the parentheses, but the curly brace on line 90.
Okay.
Okay, so it's ending actually there. Oh, okay. So at the end of your while on line 92,
Okay.
at the very end of that line, you're supposed to have an open curly brace there.
Oh, okay.
Because it's supposed to open up the loop and do everything in it. And delete that close. Yep. So try building now.
There it goes.
Okay.
Okay, I'm good.
Great.
Thank you.
Sure. Everyone else good? Okay. So so this is our function for going forward. So for instance, in int main, I should be able to say go forward 2 and a semicolon. Let's build that. If I download this to my robot and I run this, the robot should go forward 2 feet. And it should be using our nice smooth auto straightening to do it. And so if we're going to have it go forward, let's go ahead and make it go backwards as well. So
Could we not just do -2?
Negative where? Say that again.
Could we just do -2 instead of?
That's a possibility. Actually, I'm not. Yeah, why don't you try that? Because that probably will work. Actually, I think the only reason it might not work is we might have to change the signs on our autocorrecting. Well, I guess I can load it on my robot. To be able to see that better.
I was getting ready to do it now.
Okay. I'm going to try go forward. Let's try to go forward -5. Yeah. So I'm going to go forward 5 and go forward -5. And let's see what that does. The only thing it might affect is we might have to. Well, I can plug into. I forget I can just plug in the controller here.
So it went forward. It didn't go backwards.
It didn't go backwards at all?
No.
Why would that? Oh.
Do you have to change the forwards to reverses? Like, do you have to make a new
Yeah.
function for backwards?
Actually, you know what? It's not going to work that way. Yeah, because okay, if I feed in a -5 here, the only thing that -5 is going to is feet,
Position.
and then feet is going to degs. So it's only checking to see if this is less than -5. It's not actually doing anything to the spins at all.
Right.
Yeah, and we're
Yeah.
also going to have to. I mean, if yours is still geared for, mine's still geared for torque, so I'm also going to have to go back in and where it says times 360, I'm going to have to finish it off by multiplying by 7, dividing by 3. That way I could
Yeah.
fix my gear ratio because my 2 feet was like a foot.
Yeah. So you would multiply by 7/3 to if you need to adjust for the gear ratio. And you can just do that up there, just times 7 divided by 3. But yeah. So go forward -5 is not going to work. So we are going to have to write a backwards function. Because the reason why -5 worked for that movement function, because that -5 was actually being fed into like a spin 4 command. But in this case, that 5 is only being fed into like the degrees that we're checking. So
would we just copy and paste that function and to declare another function and then just change forwards to reverse?
pretty much pretty much. The only there is one other thing I want to do to it though. But yeah, for the most part, that's all we would need to do. And in fact, let's do that right now. So we're going to copy the entire function. Make sure you grab every bit of it, including the last curly brace. So let's just copy that and paste it. And we'll just call it. I might just call it go back. Go BCK for go back. And like you said, the only thing we probably need to change is just change these to reverse. Although we may need to flip our plus and minuses. We may. Because in fact, I'm pretty sure we will need to flip our plus and minuses. Because if we go through, let's go through like an example of the math again. If the left motor got ahead, but in the negative direction, let's say it had a -100, and the right motor was like -90, then that would give us an error of -10, right? And so our speed would be
Our speed would be negative already, so you'd be making it faster.
Right. Yeah, I think Josh is right. Because if you had negative
so
0.1 times 10.
yeah, that'll be well. Wouldn't our speed be 5?
Yeah, it's gonna be. Yeah, they cancel out.
Yeah. But we want our speed. If the left motor is ahead, we do want that one to slow down, right? So maybe it does work out. So maybe we don't have to change anything. So maybe it will just be fun. And we can just try it out in a second, right? And if it gets janky on us, then we can try changing those signs. Another thing we could do is instead of saying reverse, we could just say a negative speed. We could keep it forward, but with a negative speed. Well, let's find out. Let's try it without changing anything. But however, this is a good opportunity since we got to raise and lower the arm anyways. How about after we stop the motor in our go back routine, since that's when the arm's got to raise and lower, why don't we just go ahead and put that here in our go back? So I don't have an arm motor. Let me add an arm motor. I'll do an import 3. I'll call it arm motor. So in our go back function, at the end of this left motor and right motor stop, let's just raise and lower our arm. And we can just do that by saying arm motor. Let's just use spin 4. Forward. And let's just say, say I just want to raise it 45 degrees or something. So that would be 45 times 7 because of the gear ratio. And then I can just do an arm motor, spin 4, reverse 45 times 7 degrees. So that should just raise and lower the arm at the end of the go back. You know what? While we're at it, since we don't want it to immediately go forward and back, we probably want to put a little bit of weight for it to stop. In our go forward function, after our stop, let's just wait for maybe half a second before it backs up again. So that way we won't have a kick to it when it's, or it won't try to do a wheelie when it's going forward and immediately going back. And I don't think we necessarily need the weight there because it's going to actually wait around for the arm to go up and down. So we don't need an additional weight for the going back part. Let's build that. We don't have any errors yet. I'm going to go ahead and in main, I'm going to go forward for 5, and I'm going to try going backwards for 5 to test out. So I'll go back 5. And I just want to test that out to make sure that it's going straight when it does it. So let's connect. And I'm going to download this. It failed to download. And it's timing out on me now. Let me cancel out. Well,
Mine kept forward and then did the shock.
It
I
did the
can't
shot,
find my connector cable right now.
but it didn't go backwards. Is what you're saying?
No, it did not go backwards. I'm
It
trying to
just
figure out.
immediately did the shot.
Hold on. What? No. Yeah, it did 3. It went forward 3 feet, never went backwards, and then did the shot.
You know what we forgot? I know why I did that too. So when we do those while loops, what are we supposed to do before we do the while loop?
Absolute value? No, we did that.
Yeah, we did that. What do we got to do to the motor encoders before?
Oh, we got to clear them.
Yeah,
Initialize them to 0.
yeah. So we got to set those motor encoders back to 0 before we do our while loop.
So would we do that at the end of the first? Well, I mean, the beginning of the first one and the beginning of the second one.
Yeah, well, I mean, yeah, that should be probably right after we do our calculation. We probably want to reset our. Come on, sorry, I'm having to reload. Fortunately, it should have saved it. I probably should have saved it somewhere that was easier to find. I've just been dumping all this in my main drive folder, and that's not the best way to organize things.
So resetting the motors to the initial position should go right after the degrees, like with the feet times 12 business.
Yeah, that's
Like
where I
right
would put
before
it.
the loop spins.
Wait, it's this. This is not my code. This is the wrong code. Hope I didn't lose it. Try opening again. Man, it's a slow. Should be I should have a unit 9. Okay, this is it. Unit 9 activity 1. Okay, yeah. So, like after we did that calculation, like before we do our loop, we do need to reset the encoder. So we have to say like left motor dot set position, and we want to set them to 0 degrees. So what was happening, Josh, is since it was already at the target value when it was backing up, and we didn't reset that, then that's why it was kind of kicking out of the backwards part of the loop.
You did left motor twice.
Yeah, I do. Let me finish typing this and then
Can we also just do on one line of code, do left motor set position and right motor set position?
No, like you mean like say like and
Like the double and
yeah, that no because the and is actually it's actually a logical operator. It's not like a it's not a multi-function kind of thing. It's for combining different conditions together, but it's
Okay.
not for like combining like different commands together. If that makes sense, what I'm saying.
Mm-hmm.
Because listen, an operator is supposed to send back a true or false. I'm hearing you running it. Did it go backwards correctly? Is what we really want to know, or do we need to flip some signs or something? this time I download. Okay, I want to run mine. Forward is good. Oh, backwards is bad. Backwards was bad. Did yours do the same thing, Josh? Like, did it just start spinning faster and faster and faster?
So Eric, my robot is doing something very weird.
Oh, what's yours doing?
So it's doing the right direction. So it's moving forward and then moving backwards. But when it moves backwards, it moves much faster.
Is it moving much faster? But is it going backwards? Because mine actually started spinning, and it started
Yeah, okay,
spinning
so
faster.
it did that. It started spinning. So is it a thing with the KPs?
It is a thing with our signs on our directions. We do need a. We need to flip our plus and minuses. So what's happening here? And mine just did the same thing. So in our go back part, instead of like subtracting the error in one and adding the error in the other, we actually need to reverse that. Because what was actually happening here is instead of correcting, it was making it worse. And then as it made it worse, that error got bigger. And that made it, the next time I tried to correct it, it made it even worse. And so, for instance, if he had ran it long enough, it would have just spun faster and faster and faster and faster. But yeah, so we want to flip those signs. So
Yeah, that was crazy.
Yep. Because instead of correcting it and making it better, it was just making it worse and worse.
Yeah, that definitely worked.
Yep. Mine's just gonna time out again. How did it work for everyone else?
Mine's good now.
Good. Mine failed to download. Now, there are some things we left off here that were kind of optional that we've done in the past. Like we didn't actually put anything on the brain. Like we could have told the brain it was going forward 2 feet and back 2 feet. Because we've done that kind of thing in the past.
Yeah, whenever we were doing the math earlier, so the error at the beginning, yeah, it was going to be negative, but whenever you add a negative to a negative, you get a bigger negative. So it was still speeding up, like we talked about the left motor. And then whenever you add a positive, because the negative gives you a positive, whenever you add that to a negative, it gives you a smaller negative. So it was slowing down. And so that was what I was saying, like about the switching the signs. Whenever you asked if we needed to do it earlier, that's what I was getting at.
Yeah. And mine just won't download.
Mine did that for a second. I just had to unplug it and plug it back in. I don't know if yours is.
Yeah, I'm trying to do the same thing. So I unplugged it. I want to try turning my brain off and on again too. Um, if we wanted it to show up on the brain, it wouldn't be hard to add that in, right? Like that could be like one of the first things we do in our function when we declare it. We can just say brain screen print. And we could say go forward, and I'll just say present D, comma, feet, because or present D feet. and then it'll display the feet there, and then we can just do a brain screen new line. And then and we could just copy that and put that in our backwards function too. But instead, we can just say go back that many feet. Let's see if it'll download this time. Oh, okay, it downloaded. Oh yeah, that worked out really nice. Except for I get my arm direction wrong. Well, I can move my.
Yeah, I found that out yesterday. So I have my motor set up on the left side if you're looking at it from the back.
Mm-hmm.
And so I guess like we do for our left motor on the other gear train, you got to do the reverse deal.
Where's my? Oh, that's it. Also, I have my arm plugged into port 2, not port 3, and so I was wondering why it wasn't running it. Let's try it now. Forward and back. Yep. Okay. Now it's working. Yep. Okay. So mine is working really nice now. And now that we have our functions and they're all working right, now to do the actual basketball drill, all I need to do is say go forward to and go back to, and then I can copy that and go forward 4 and back 4. And go forward 6 and back 6. And then go forward 8 and back 8. I guess if I wanted this prettier, I'd do some white space. And
So the one problem that I'm having is not a problem that I think we can do anything really about unless we just slowed the motors down for the arm whenever it shoots. Because the arm, whenever it's going up and down, is bumping the robot over one way or the other, usually to the right.
Yeah, I'm slowing mine down on the whole like thing because I don't know if it's the floors that I've got, but it's I don't think that it's a problem with the code. I think it's going fast enough. It's having so much error that it's overriding. So I'm gonna slow my whole system down.
Okay. Yeah, and fortunately, we have a nice variable for that. So you could just set that 6 to like 4 or something.
But that's not in the arm motor part, right?
No, that's true. So if you're talking about speeding, slowing down the arm
Yeah, we would have to set spin.
or set velocity, yeah. Because we're using spin 4, so you're going to have to use set velocity because spin 4 doesn't let you control the speed of it. But I was overall happy with mine. And it even displayed it on the brain. It went straight forward and back and did it all. I didn't measure it. And like I said before, like in class, I would just have tape lines on the floor so they could set it up against the tape lines and run it.
Making mine slower helped.
Oh, great. Yep. How was everyone else?
I'm having some trouble with my wheels staying like straight, I guess is the right way to say that. Like the little plastic piece or whatever that goes into the wheel keeps coming out if I run it too long.
Okay.
Like this.
So
It's like in there.
oh, that okay. Okay. If you have rubber axle collars,
Mhm.
you could try to put a rubber axle collar on either side of that
Okay.
to make sure that kind of stays in place and won't
Okay.
slip off. Yeah, that's probably what I would do if those inserts were slipping out.
I have the same problem, Ashley, so you're not by yourself.
One small issue that I kind of noticed with mine is the auto straight while I was driving was great, but when I got to the end, it still had a little bit of drift. Uh, when it was like stopping, did any of you guys have that issue or?
I had it to where like whenever it would go to reverse, it would like one motor would slip and then from there it would get like when it first started the motion, it would slip a little bit. And I think that's where it kind of got a little wonky, but I could definitely see the auto straightening try to happen.
Yeah. And one reason mine's drifting at the end is because my battery cable is actually up against one of the wheels on one side. And so that's causing more friction on that side.
Yeah, same with me. My battery cable is on one of the wheels, and then I also kind of figured that because the wheels were a little bit like wonky,
Mhm.
then that might account for the drift too.
Yeah.
Yeah, those axles start to, or the axles start to bend, those shafts start to bend after a while. There's really like, unless you just want to switch those out, it's kind of like, eh.
Yeah. That's also kind of why it's a good idea to have like a rail on either side of the axle, because they'll definitely bend if you don't have any support uh, on both sides for the wheel. Like if you just have the wheel on the outside of the axle, yeah, you'll definitely end up with a lot of bending there.
All right. Mine worked. We could add that smooth acceleration and deceleration that we did the other day.
Yes, we could. Yeah, we definitely could if we wanted to, and it wouldn't be that big of an issue. Um, Now the the adjusting the speed with the acceleration and the auto correcting at the same time will be kind of interesting.
Is there a way whenever we're looking at our code, there's not a way other than us printing it every time or something like that for us to go back and look at each iteration that we did, is there?
No. So if you want, yeah, because it's just auto saving. It's auto saving every time. So and it's just saving over. So
Right.
so if you have different iterations, you're going to just need to save them as different files, but you'll have to do that manually. But yeah, it doesn't keep up with a history of your revisions, unfortunately. Um, um,
So I
so
ran mine, but it ran a little better now that I have put those silver collars on. So my wheels, instead of the rubber ones, so the
mhm.
wheels are staying more intact. So it's still got a little wobble, but it kind of
Yeah,
veered a little bit, but it did go forward and backward the
mhm.
supposed to.
And you should see as it's running, it is actually trying to correct sometimes. Like you'll see it kind of like move slightly every so often to try to correct there. So it should go relatively straight. And then uh, you're not going to be able to get it perfect. So there, at some point, and there's going to be some kids that are going to want to go perfect with it. At some point, you're just going to say like this is good enough. So otherwise, you could have these kids spinning their wheels for they could like spend an extra week on it and still not get it perfect. Um, so at some point, you're going to just have to say, okay, hey, it went forward and back, and it was relatively straight. So great job. and
That would
and
be
let's.
me. I would be that kid.
Well, I think some of my problem too is I have a tile floor and my grout is real wide, so it probably messed with it a little bit too. So
Yeah,
at school I'll have the playing field, so it should be pretty smooth.
yeah. Come to think of it, my floor is kind of textured too, so that also is probably introducing some problems. Yep. Okay. Well, let's move on because we still actually have a good bit to do because we were actually supposed to go over 9 and 10 today. And we haven't finished going over all 9 yet. So we kind of got it bogged down with the first assignment a bit. But as long as we're learning a lot, that's important. But I don't want us to miss anything either. So we're going to hop back in and we're going to look at 9.2 where we're going to introduce the bumper sensor. So here are 2 sensors here, and this is the older version 1 of the bumper. Notice it doesn't have a little screw in the center. The version 2 has a screw in the center that you can actually, so you can actually like mount stuff to the button. So, like for instance, you can like if you wanted the button to trigger like across like a wide area, you can mount like a bar or a plate to it, which is kind of useful. And then here's that limit switch, like the one that Ashley was showing off. Notice, Ashley, this limit switch actually still has its metal tab on it. I don't think the limit switch you had, it looked like the tab was broken off of it. But that metal tab is flexible. So basically, since it does flex, like say if an arm were like coming down onto this, even if it went a little too far down, it's okay because this is flexible and it'll just kind of spring back. And so, and these limit switches are much more sensitive to trigger than the bumper sensors. But that's what we're going to be looking at today. Bumper switch. It's a digital sensor, like Ashley did and Raven both did in their presentation. It is a digital sensor. Um, so there is a pressing function, and that pressing function, when we call on it, um, it's going to return true if the button's being pushed, and it's going to return false if it's not being pushed. And so we use it for things like if the robot's hitting a wall, or if we want maybe we can put the bumper on top and use it as a button to maybe start our program. Uh, so we can do things like that with it. And then the limit switch is basically just like the bumper switch. It's still a switch. It's just as a little more sensitive, and it works the same way. It's true if it's being pushed, and it's false if it's not being pushed. Um, you typically use this to limit the motion of something. So, like for instance, if we had an arm that was coming down and we didn't want it to go down too far, we could maybe put that limit switch there. So when it reached it, it would trigger and it would click it. And so to set these up, we would click on the 3-wire, and then we could pick out whether it's a limit switch or a bumper switch, and then we set what port it's in. And these all plug into the ports on the side, the 3-wire ports that are on the side there. Those are called legacy ports because they're kind of a carryover from the old equipment. The stuff before V5, everything plugged into those and the old stuff. So that's why it's a legacy port. So if we were trying to say write a flow chart that says to move the robot forward 3 turns when it's pressed once, this is what that flow chart would look like. So that'd be like if we put the bumper on top of our robot, and so when we press it, it moves forward. So is it pressed? No, then we're not going to run it. Otherwise, yes, we are. Now, one issue with this flowchart here is it's not going to wait around and keep checking, because this is not drawn as a loop, because notice it doesn't come back to the start again. So that means that if you wrote a program like this, as soon as you start it, it's going to check to see if you are pressing the button. And if you're not, then it's just going to move on. If you are, then they'll go forward. But it's never going to check again. It's just going to check that one time. So if you wanted it for instance, to say wait around, then what you would probably want to do is maybe loop. If it's being pressed no, then let's loop back here. And then for our yes being pressed, do this and then continue with the rest of the program. So maybe just attach this continue rest over here, and then for our loop, just or for our no, just loop it back around. So there are a couple of things that we have here. What we're mainly going to be using is pressing. And pressing is going to return a true or a false value. Uh, if it's being pressed or not. So if it's being pressed, if you're doing pressing and it's being pressed, it's going to return a true. Otherwise, it's going to return a false. Now, there are two other things you can do, two other functions you can use other than pressing, and that's pressed and released. And those are what are called callback functions. So what you would do is say if you use like say bumper A pressed call out. What you would do here is where it says callback is where you would like put in the name of a function. And so if you did that, basically every time, and if you put the bumper A pressed in your code, and say maybe your function that you're going to call on is like maybe move forward, then every time the button was pressed, it would run that move forward function. Similarly, when you can do the same thing, but work when the button is released, you can call back and maybe call on that move forward function. And the difference between the pressed one and the released one is the pressed one will run as soon as you press the button. The released one will wait around until you let go of the button, or until it's so like it's being pressed, and then it's as soon as it's not being pressed anymore, it's going to run. So, for instance, if you were setting up as a button to start your robot, you might want to use the released instead of the pressed, because it'll wait until you remove your finger from the button before it runs the function. Now, in our case, though, we're probably just going to be using the pressing, and we're not going to be doing the callback stuff. So we're just going to be using pressing here, and that pressing just returns a true or false back, whether it's being pressed or not. So it's not actually going to be calling on a different function or anything like that. So here is it being used as a callback here. So this is the bumper pressed. So in this case, notice that this is not part of any condition or anything. We're just saying bumper A pressed, and then we're going to do this press function. So basically, if we do it this way, it's going to wait around until the bumper's pressed, and then when it's pressed, then we're going to run this function here, which is pretty handy.
So that's like if it ran into the wall and it's like, I ran into the wall, I'm backing up.
Yeah. So we can make a function called like say backup, right? And then actually that's what this function does. Now I'm looking at it because it's backing up 3 turns. Yeah. So one thing we could have done is we could have maybe had a motor spin forward before this function here, and then when it's pressed, it's going to then run that backup function. So one thing to point out is when you're calling on a function, notice that you don't. So normally when we like use a function, we put a parentheses for the function, even when we call on it. You don't do that in this case. You just put the name of the function. You don't put parentheses out to it. And here's the same thing with released. Same thing. The only difference here, this wouldn't work so good if your robot was if your button was on the front, because if it ran into the wall, it's not actually going to back up until the button's no longer being pressed. So that wouldn't be super useful for if the bumper was on the front of the robot. But this would be perfectly fine if you wanted to back up. If you had your bumper on top and you were using it as a button to start that routine. And so, what's this say? So write a flow chart that says move forward as long as the bumper's not pressed. That's what this is. So is it being pressed? No. Then we're going to run forward. And then it's going to check. Is it being pressed? No. We'll keep on running forward. Is it being pressed? Yes. Okay. So let's kick out of the loop and stop our motors. And so this is one way we can write that. So while the bumper being pressed is equal to false, then we're going to go forward. And then once that becomes true, true won't be equal to false, and that will kick us out of the loop. And then we can stop our motors. The other way we could have wrote that condition, instead of saying bumper A pressing equals false, we could have just said while not bumper A pressing. Well, using that explanation point. Okay, so another function that's built in is this wait until function. However, I don't think it works like it used to anymore, because you can find wait until if you go into control. There is this wait until, but when you actually drag it over, it doesn't say wait until anymore. So like if I drag over this wait until function, it changes it to while not conditions true, which is kind of weird. So I don't think that works like it used to. But there was a time where you could, well, maybe we can type it out. What happens if we do type out? I'm just going to type it here just to see where. Do we have still wait until? And
When you click
maybe,
on it, it changes it automatically to the not to the exclamation point.
okay. Yeah. So I don't think that's a thing anymore. But really, that's what the wait until was doing, anyways. It was just doing a loop while it wasn't being pressed. So we don't necessarily have to worry about that. Maybe we should not even consider that slide then. Now, in this case, this is going to run in reverse while the bumper is pressed. But and in this case, so if we had a code like this, while it's being pressed, it's going to set the spins to reverse. We're not actually, when we kick it out of the loop, we're not telling it to stop afterwards. So I guess in this case, if we had some spin forward in front of this, once that bumper was pressed, it would spin in reverse. And since we're not telling the motor to stop, it would continue to spin in reverse. This way. And so we could have a Roomba. We can make the robot like a Roomba where we put a bumper on it, and as it goes around, we can bump into something and then maybe back up and turn a random amount and then go forward again until it bumps into something else, and then it'll back up and turn another random amount until it just bounces around the room that way.
This is why my floors have streaks on them when it mops.
Yes. Yep, because it's not like doing a nice pattern with it, is it? So I think I've seen some of the fancier.
It does
robotic-
circular streaks. It tries.
Yeah,
It did a great
It
job.
it does an okay job.
yeah, better than nothing, I guess. So let's introduce how to do a random number. Because if we want to turn a random amount, it would be nice if we could generate a random number to turn a random amount. Now, it is actually really hard for a computer or any sort of electronic device to make a truly random number. Because when you think about it, true randomness is actually kind of hard to pull off. So instead, what we can do is try to approximate a random number. And one way we can do it is we can use this command to create a random seed. And the way it's it's looking at the timer on the brain, because like when you turn on your brain, it actually keeps up with the time, how long it's running. And in this case, it's going to look at it at the highest resolution possible. So that means that timer with a bunch of digits. So not only like milliseconds, but well, however far it can go. I think it can go to like 100th of a millisecond. And what it can do is, if you're looking at that time that's counting, and if you're looking at the very last digit of that, like in the hundredths of a millisecond, that digit is changing so quickly that it might as well be random. Because like if you were trying to stop the timer at any given time, it would be really hard to, every time you stop it, to always stop it on the same last digit. Just because that digit's just changing so fast. Does that kind of make sense? And so basically that's what this line of code does right here. It's grabbing a seed for the random number, and it's generating that seed by using this number that's changing so fast that it might as well be random. Because anytime you try to like stop it to take a snapshot of what that timer is, you can't just like stop it on the same place every time, because that timer is just changing so fast when you look at it at its highest resolution. So that is generating the seed, and it used to be we would actually need this line of code to generate the seed. However, I don't know what update did it, but at some point, VEX Code had started doing that for you already. And in fact, it generates that seed even better than what we're doing here. So if we look at our VEX Code, am I sharing my screen, by the way? I am. Okay, good. If we look at our VEX Code, remember all that hidden stuff in this pragma here? If we reveal that and kind of look through it, somewhere in here, oh yeah, so here is it generating, here's some code that it automatically does to generate random seed. And not only is it looking at the system timer, but it's also even grabbing things like the current flowing through the battery and also the voltage flowing through the battery. So, because those are not going to be consistent either, and it's measuring it all the way to like the millivolts here. And so, the seed it's putting together is it's taking the system time at its highest resolution. It's taking the voltages, which is always kind of fluctuating a bit. And it's taking that current, which is always fluctuating a bit, and it's putting all that stuff together to come up with that random seed. So it's using all kinds of different things that are changing a lot, and putting all that together to make it an even more better approximation of randomness. And that's how it's generating this random seed here. So that's how it's coming up with it. And so anytime you start a new code, it's doing that already in the hidden code. So we really don't need this srand anymore, because it's doing that already, and it's actually doing a better job of generating a random number. So you can kind of ignore using this line, but this line is important. So if we want to make a random number, in this case, this random number is going to be an integer. The way it works is you call in this function rand, and this rand, it starts off, rand is generating a number from 0 to 1. But this %10 is actually doing a modifier. Well, and I say 0 to 1, but it's not actually 0 to 1. It's 0 to almost 1. So it's 0 to like 0.999999. So almost 1, but it never actually gets to 1. However, if we do this %10, this %10 is like a modifier to rand, and this kind of sets the range of the number. So if you think about it, so this is going to go from 0 to almost 1 is basically what this is doing. So in integers, well, okay, so basically this %10 is actually changing the range of it. So instead of from 0 to almost 1, it's going from 0 to 9, which 0 to 9 is actually 10 numbers, right? Because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this number here kind of sets the range. And then this last number here kind of sets the offset. In this case, we're adding 1 to whatever we get. So originally it was 0 to 9. Now it's 0. Now it's going to be 1 to 10. So this would give us a random number between 1 and 10. So what we would do is we'd say rand, and then we want the range of our number, how big a spread we want, and then what our offset is. So what if we wanted a random number between 1 and 100? Well, then it would just be rand percent 100 plus 1, because our range of values, we want 100 values, but it's going to start at 0, so we're going to add 1 to that. So that'll be a 1 to 100. If we did just rand %10 and just plus 0, or didn't do the plus at all, then that would just be a number from 0 to 9. So this is a slide provided by David Bennett. You might remember him from the from when we did our blah blah blah. What's that called? Our refresher, when all the veteran teachers joined. So he was on the line, and he spoke a lot. So he kind of wrote this slide out, and I think he also wrote this slide out too, to try to explain. Yeah, I think he did all these slides. Yep. So I kind of threw these slides in that he provided to and these kind of explain that random number thing. And particularly, that's the range, and that's the minimum value. I usually call it the offset, because that's how much you're offsetting by. But it would be a good idea to maybe have the kids kind of work with, maybe like kind of like give them some targets, and like what would be the range and minimum, or range and offset you would need to get that range. So for instance, an example here, if we want a number from 1 to 10, The range of that is going to be what are they saying here? It's the difference between the largest and smallest number you want plus 1. Okay, so if we want to range between 1 and 10, that would be 9 numbers and then plus 1. So that would give me a range of 10. Or between 2 and 7, then the range is going to be 6. And the min is the starting number. So in our case, we might want our robots to, say, back up a bit and then turn a random number of degrees, right? And we might want that number to be both a negative or a positive number. So for instance, if we wanted a range of, let's say our values between like negative 90 and 90. So when it's backing up, it could do like a 90-degree turn to the left or a 90-degree turn to the right or anything in between. What would be my range of numbers that I would need? What would I need to set for my range?
$181.
Yeah, my range would be 181. And then what would be my minimum?
Negative 90.
That's exactly right. And so if I put my range for 181 and my minimum 90, then that's going to give me a range of values between negative 90 and 90. That's exactly right. And so here is some code. So here we have this movement function again, and it's doing the same thing it did before. It's got a turn distance, and it's got a left and right speed. Here, now once again, you do not need this line 33. You don't need to set up the random seed anymore because it does it automatically. So you don't need to worry about generating a random seed anymore. But then to make our random number, we do still need to store that random number as a variable. So in this case, it's going to be, this is going to be a number between 1 and 10, right? And then it looks like it's going to be, if we're using movement, it's going to back up 5 turns. And then because since one of these is negative 50 and one of these is 50, the speeds are in opposite directions. That's going to be a turn. And it's going to do a random number of turns here between 1 and 10 turns. And so it's going to turn a random amount. Now, in this case, it's always going to be turning in the same direction. But it depends on how much it turns. If it turns out like 10 turns, for instance, makes it go more than 360 degrees, which it very well might. It might actually go a lot. It might just be doing like a several laps around before it stops turning. And since this is set up in a loop, that means this is going to just repeat, and it's a infinite loop because it's just while true. This is just going to repeat over and over again. So it's going to back up, turn around to amount, back up again, turn around to amount, back up again, turn around to amount, and it's just going to do this over and over and over again. So just go forever. So that's kind of how we can use our random a bit. And once again, we can also write some code if we print our random number. So let's say we generate a random number. Then if we wanted to print it, we could do like we've been doing. So like we could say %d. that would be the integer, and then we could just say what the random number is, and we could make that show up on our screen if we wanted to, which is not a bad idea. So let's see what this is right here. So I think this is a video of what it would look like on your brain. So this is kind of showing that every time the button's being pressed, it's backing up and generating a new random number every time. And it's using that random number for its turns. Yeah, so that's kind of what was going on in that picture there. And once again, showing the output on your brain is really useful for debugging things. So also, if we were interested in adding like a function to actually pick up stuff, we may want to consider adding like a conveyor belt to our robot. So this is actually the tank tread kit. I don't think everyone has this kit because I think this is an optional kit you can buy. So it's very likely you don't have, like, for instance, the bogey wheels or these particular tank gears, but you probably have some sprocket and maybe track. Maybe you just have sprocket and chain. But then you have these, basically you have this tank tread track. If you buy one of these optional kits, you can have that. This is the layout you would kind of do. So like one of these wheels would be powered with a motor. One of these, well, gears, I should say. Well, not gears, sprocket is a sprocket. And if you're trying to do, instead of wheels on your robot, you could set up a tank tread on your robot, and you could kind of probably set it up like this. And one reason they kind of have it this way is, for one, basically the wider the surface you have, the more friction you have. And the more friction you have, the harder it is to turn. So they kind of like cut down the friction a little bit. Another thing is this allows it to kind of rock up and down. So like, for instance, if it hits an obstacle, it will allow it to kind of like rock up a bit to get over that obstacle. And so that's why you generally, if you're trying to build a robot with tank treads, you would kind of go this shape on the side of it. Now you can use other things for those tracks too. Some of the tracks allow like these flaps to be inserted into them, and the flaps come in 3 different sizes, but they're just like little rubber flaps, and that can be handy if you're trying to build a conveyor, because you can like use the flaps to push something along a conveyor. Is there a picture of that? No, there's not. So what you could do, for instance, is maybe you have some ping pong balls in the field, and you want it, as it's going around like a Roomba, to maybe suck up those ping pong balls. So if you had like a conveyor running, it could, and with those flaps, the flaps could maybe hit those ping pong balls and pull them up the conveyor. There are honestly better ways to do an intake like that other than using flaps, though. A lot of teams, like when you're picking up objects, like for instance, the objects in this case, what they might actually do is they might use 2 sprockets, but then like put rubber bands between the sprockets. And those rubber bands have a lot of flex and compliance to them. And so no matter what the shape of the object is kind of pulling in, the rubber bands can kind of form around it. And so you kind of see that a lot of times for intakes instead of conveyors. So once again, you do not have to have the kids do this, but if you have the materials to do it, you could have them pick up something like ping pong balls or something on the floor, especially if you have extra time and the kids want to build something extra, and not just mount a bumper. So here, so if we look at this activity, we want to create a robot that mimics a Roomba. It will need to have a belt that moves to simulate vacuuming the floor. When it bumps to a wall, it needs to spin some random number of degrees away from the wall and then continue to move until it bumps another wall. And it says you must use functions to create this code. So that's the I believe that is what if we go to lesson 9.2. There's a couple of activities. There's 2 activities here. Let's see what each activity is. So this one's the Roomba one that we just went over. And this other one, let's see what this other one is. This other activity is a simple limit switch. It says using your system robot, add a limit switch to the high point of the arm motion, create a stopping mechanism for raising the arm. And it says update your basketball drill code from lesson 9.1 activity so that the arm is not controlled by a certain number of degrees, but moves until it hits the limit switch. And then the down motion can be controlled either by degrees like previously or by using a second limit switch to control the down motion. Honestly, as far as mounting goes, depending on how your robot built, it might be kind of hard to mount that limit switch for an upper position. It should be really easy to mount it for a down position, though. So you may want to have them. Like this robot here, it would be really easy to put a limit switch right here so that when this came down, it could touch that limit switch. And so, but as far as, well, I guess that's part of, a build. As far as like telling it when to stop, when to come up, you would probably need to mount like some additional metal up here so that that limit switch would have something to attach to. I don't see any other way around that, because, or if you wanted to, maybe instead of mounting it up here, like in this case with this arm, maybe you can mount like some standoffs coming out the back of it, and then have the limit switch come out off of those standoffs out to like, say, like out here or something. And so it would only raise up until like it hits right there. In which case it would just be a matter of, well, you could, in that case, you could put 2 limit switches on if you have to give to each kid. So you could have it just raising up until it hits the upper one, and then lowering until it hits the lower one. What would that look like in code? Well, fortunately, we have a basketball code. And really, what would be changing is we wouldn't use the spin 4 command anymore, right? For our arm rotors. Instead, it's only going to raise up until the button's being triggered, right? So we would probably have like a while loop for it, right? So I'm sorry, I'm not sharing anymore. Let me share my screen again. So this is that basketball drill, and I thought we were done with our basketball drill. Now I guess one more basketball drill. So here is this is in our backup function where we were raising and lowering the arm. So instead of raising it and lowering it for a certain amount, what we can do is raise it until a button is triggered, and then lower it until another button is triggered. So how would we go about doing that? Well, what we could do, first off, is we probably need to add a bumper in. So we'll go into devices and 3-wire, and let's add a limit switch. I'll put it in A. And honestly, if we want to control both the upper and the lower, we could probably add 2 of them. And maybe I should name them that way. I'm going to call one like upper limit. And I'm going to call the other one lower limit. Mm. And how about we make this raising and lowering stuff its own separate function? So let's create a new function that go back will call on when it's time to raise and lower the arm. And so since go back is going to call on that function, I need to put it above go back. And I might as well put it in front of go forward too. So I'm just going to, it's going to be our first function we're going to make. And let's call it, what would be a good name for it? How about shot? Because that's kind of what we're doing, or similar to shot. Does anyone else have it, or shoot?
That's fine.
Okay, so we're going to call it shoot. I don't think we're going to need to feed any parameters into this, so we're not going to put anything in between the parentheses. And so we're just going to write a function called shoot. Oh, it didn't mean. Let me unplug the brain. Let me time this up.
Out of curiosity, since you don't necessarily know when it's going to stop, how would you put in a number of degrees? Because it said the second option, or one of the options, was you lower it by degrees. How would you know how far to lower it?
Yeah. You just have to, in that case, you would just want to pick a degrees where it's not like running into the lower limit. So for instance, and honestly, it might be easier if you just modified this assignment to just have a lower bound, I guess.
I mean, could you have it where it knows what the set position was and then it can return to the set position once it's no longer pressed?
Yes, you could do that. Did we want to write it like that?
That makes sense.
Well, and we would be able to we can kill 2 birds with 1 stone here. We can work on the function to shoot it with the limit switch. And then rather than requiring the exact same code again, or some version of the same code, we could do a follow-up. What would happen if you wanted to do it the other way?
Okay. Yeah. So, well, I'll leave this lower limit in, but let's just try to do like what you're saying. So this is going to be a little more complicated. Hope you guys don't mind that. But basically, what Josh is saying is it's going to rise up until it hits that limit switch. But then when it's time to lower, we want to kind of like use what we did for the upper limit. However far raised up is how far we want to lower down. So basically, we need to kind of grab that value and store it, and then use it, right?
Yes.
Yep. Yep. Yeah. Okay. So we can do that. I'm sure we can do that because we're smart people, right? So used to be. Okay, so where do we want to start first? Well, we need to raise it up until it hits the upper limit, right? So that's the first thing we need to do. And probably the best way to do that would be to do a loop, right? And so like while the upper limit's not being pressed, so we can say like while not upper limit pressing. So while it's not being pressed, we're going to raise the arm up, right? And to raise the arm, we're going to say arm motor spin. It's forward. It forwards up.
So the reason you're not using the spin 4 is because you're using the limit switch to basically cut you off. So you don't need to have a certain number of rotations. It just goes up until it hits the switch.
That's exactly right. Yeah.
Right.
And then we're going to want to stop our motor. It probably wouldn't hurt to do a hold. So set our arm to hold. Though honestly, it's going to probably immediately lower it back down again. But set stopping. And let's set it to hold just in case. And then arm motor stop. So that's going to raise it up because it's going to, while the button's not being pressed, it's going to spin the motor forward. And then after it's being pressed, it's going to kick out of that loop and it's going to stop that arm motor.
And I went ahead and tacked on whenever we did the spin forward at the top, arm motor spin forward. I went ahead and took it to 25%. That way it doesn't throw off my robot.
Okay. You set a speed for it of 25%?
Yes. Well, that's what I did. I don't know what everybody else wants to do.
Oh, I mean, we could do that. Doesn't hurt anything. Now, if we want to keep up with the value of that motor, what we probably want to do is first off, let's go ahead and set the motor position of the arm motor. Let's set it back to 0 first before we raise it. So arm motor dot set position. And we're going to set it to 0 degrees.
Before we jump in, quick question.
Yeah.
Could we not just underneath that, whenever we want it to go down, just say motor spin to position and then tell it 0 degrees again
Yes,
without
that
having
is
reset anything?
that is true. There is a spin to position command, and we could just use that. So we wouldn't. Yep. Yep. So we could just use that. And in fact, I guess since that tool's available, we can just use that. And that's how that works. If we click on this, yep, it tells it to travel to a specific position. So we should just be able to tell it to go back to 0 degrees. And
Nice.
yep. Yep. So we could do that. And obviously not left motor, the arm motor. And that's actually probably all we would need for that chute, right? So it's going to, while it's not being pressed, it's going to raise up. When it's pressed, it's going to stop. And then it's going to spin back to the original position. So yeah, that should work just fine.
That's pretty streamlined. That's pretty good.
Yep. And so now, back in our go back function.
Can you go back up real quick?
Oh, sure.
I'm sorry. This is the first time it's come up that I've actually noticed it, at least. So whenever we do camel case, where it says spin to position, so it's every word after the first word is capitalized, not like
Yes.
alternating. Okay.
Yeah. Every
Because
word.
I just kind of assumed it was alternating, so it's going to be every word after the first word is going to be capital. All the first one's lowercase. Okay.
Yeah. So that way you know the breaks between the words. Yep. So we have our. Man, I didn't do my camel case right, did I? This upper limit. I probably should have done a lowercase u. But okay, so we have this chute that we made. It's a function. Now we just need to call on that chute. So back in our go back function, after we stopped our motors, instead of raising and lowering an arm this way, we're just going to call on that chute. So we're just going to say chute here, and we need those parentheses. And so when we call on chute, that should do everything that chute does. I would be careful about testing this code if you do not have a bumper or a limit switch on it, because that arm's not going to stop unless.
You could, without mounting it, you could just have a bumper in
Yeah.
your hand and do it that way.
Yes, you can do it that way for sure. And by the way, it says limit switch here, but you can plug in, if you don't have a limit switch on you, you can just plug in a bumper, because a bumper and a limit switch, they are physically identical things. Well, they're not physically identical, but they're both switches. So the brain's not going to know the difference between a bumper and a limit switch. It's just going to be looking to see if that switch is pressed or not. So yeah, that ended up not being so bad to do, right? Not bad at all. I think the biggest challenge to that is just the physical challenge of getting that limit switch mounted somewhere where it will trigger the arm. Yep. Okay. What about the other lesson in here, the Roomba code?
Can we
Is
take a
that
quick break?
something? Yeah, we can take a quick break. What? You guys want to take a 10 minutes?
That's fine.
Okay. So, how about we take a 5-minute break? Because there's still some stuff we want to cover before 1 o'clock. So, 5-minute break.
I don't know if you have this problem in your school, but my school, well, my school system, I guess, they have a huge issue with AI, and basically they think AI is bad. Uh, and so they do all sorts of stuff with our firewalls and everything to limit and get rid of AI as much as possible, which became a problem for me this year because they added a lot of these protocols not 2 years ago, but this past year, and I was unaware that they got added. And so we have a lesson in the principles of engineering class where whenever we're going over the coding part of it, where we have to do AI. Like that's just a part of what we do. There's like a whole section where we teach like biomimicry and like several different things. And so I try to get the kids lined out and everything, and I'm like, okay, so we're going to go to this site, and it's worked perfectly for me. Like it worked the whole year before, worked all summer, all that stuff. And then we type in the site, and it kicks back that we can't go. And I'm like, they first told me because I was kind of watching them, so they first told me that it wouldn't let them go through, and I was like, no, hold on, that works. It works perfectly fine. So I go to my account thinking not going to be a problem at all, and sure enough, it don't work. And so so then I had to get them to like I had to prove to them that it was on the curriculum. Hold on one second. I'm sorry. Okay. Sorry. Somebody had to bring me some report cards. I'm the athletic director too, so they were bringing me the report cards, and the door was locked.
Yeah, and so even the teacher accounts, it was banned.
Yeah, it banned it from everything. And so I was sitting there, and I was having this conversation with one of the tech people, and they were like, "Yeah, we can't fix it." And I was like, "Why?" Because this needs to be fixed. Because I have to do this. It's like a 4-part lesson, like 4-part unit. and they're like, well, I mean, it just they don't want us to have. I said, well, is there anybody I can talk to? So I ended up talking to basically the guy who's in charge of all of that at the school board. And he's like, well, look, just do me this favor. Send me whatever information proves that this is a part of the curriculum. And I'm like, I have to prove to you that it's a part of the curriculum. You don't just trust me, but like seriously. So I had to send him all the information and send him all the stuff. And he still sent back, like we got to be careful with this AI stuff and all this. I'm like, it'll be okay.
What does he think's going to
It'll
happen?
be okay. Like all I'm going to have the kids do is they're going to go to a website and they're going to try to they're going to make their robot be able to tell me if they're holding up a calculator or not. Like this is not like some kind of crazy, oh my gosh thing that we're doing here. It'll be okay. And I'm so ultimately it got back okay, but it was just frustrating. It's like, why is this a big deal? This should not be a big deal.
Yeah.
I mean, the guy. Don't get me wrong. The guy who I had to work with, he's a cool guy. I like him, but it's just he's following orders from people above him. And
Yeah.
gosh, man, this is just it gets old. This being scared of anything technological, and like the kid, whenever they make a big deal about the kids having cell phones, and I'm like, y'all do realize that those cell phones do so much more than probably 95% of our equipment, right? Like, and they have them in their pocket, and we don't utilize them because they might Snapchat something stupid to somebody and make somebody feel bad. And I'm like, come on, man. Like they can write a note. It's the same thing. They used to do that. That's how we did it back in the day. Like if you wanted to pick on somebody or you wanted to communicate with somebody, you wrote a note. Like it's just, I guess now it's instant and everybody can see it maybe. I don't know, but it just frustrates me sometimes.
Like our school is actually requiring like clear backpacks next year to keep to make sure the kids aren't smuggling cell phones into their backpacks. Yeah.
Instead of using them, which just makes a whole lot more sense. I mean, my thought is this: why not have a designated spot on the desk that the cell phone has to sit? And so now, if you can see the cell phone, you can tell whether or not the kid's on the cell phone, and what they're doing on the cell phone because it has to sit in that spot. And then whenever you need to actively use it for something in your class, you use it.
Yep.
Because I have a stand in front of the door policy where whenever we're doing something that needs to be videoed or whatever the case may be, that I don't want anybody who isn't in my class to see. It's like, okay, I'm gonna stand right here. Y'all get done what you need to do. Because like in physics, I don't have 9,000 things to go record data and all that stuff with. So hey, you have a really, really intelligent calculator in your pocket. Why don't you take it out and use it?
Yeah. Especially, with the phones, you can kind of go frame by frame for like, it's like velocity measurements and things like that, which is
absolutely
useful.
Yeah, there's all sorts of stuff they can do with them.
Yeah. Even if I'm watching the hallways, so we have like we have a bunch of cameras in each room. Like I think we have like a camera in every corner of our room. And administration does periodically look in on those too. So it's like with our like last year with our robotics kids, like I had some seniors and they typically go home early, but they wanted to stick around to work on stuff after after they were done with classes, but it was still technically school time. But I got chewed out over that because some of them had their cell phones out, even though they were done with school, but they were still on campus, and I had let them have their cell phones out. So and so I got I got reamed out for that. I was like, geez.
Yeah, I get it that there are certain people who are going to do bad things, but it doesn't matter what it is that we're talking about. There's always going to be certain people that are going to do bad things.
I will say though, I did see this year, we were pretty strict on it this year, but I saw that the kids actually had more conversations with each other. Like there was much more focused learning within the classroom because they weren't constantly like looking at their phone, trying to get to their phone, because it had to be like it was on lockdown. It was inconvenient a lot of times.
Mm-hmm.
But at the same time, like seeing their level of conversing and discourse, especially in those like big discussions that we would have like in AP environmental, I got much more like participation and they were actively involved in that. So it's kind of like a catch-22, but I don't know.
Yeah.
I enjoyed them not being addicted to the cell phone during the school day.
Yeah. Well, I mean, and I really don't want them on it at all in the class, unless it's something that they're trying to do. Like, for instance, like what Josh was saying, like if you're trying to like take measurements, it's really useful just to have that phone camera to 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 measure things like that, or unless you're using it as a tool for something. But yeah, I agree. I don't like it in the classrooms either. I don't like them being distracted like that.
Yeah, I wasn't
But
promoting having cell phones just to have for cell phone's sake. It
but
was more of using the
yeah,
tool.
yeah. But our school is kind of moving that to the policy that they're not even supposed to bring them to school, which that doesn't that puts a lot of, like, they're not supposed to bring them into the school building. Um, and it's like, well, what about these kids that have, like, say, practice after school and stuff like that, and they need to call for rides and things. So there's a lot of practical issues with that. And then and like I said, with those seniors, they were not in class. They were just it.
That
It
seems a
would have been
little extreme to me.
Yep. Yep.
Sorry, I didn't mean to start something.
Yep. Yes. Uh, but what was okay? So, um, I do feel kind of bad that I've been taking up so much time with this stuff, and not giving you guys a lot of free time for your asynchronous stuff. But on the other hand, we've basically been doing the asynchronous activity together. So there's
Positive
that.
catch 22.
Yes, a positive catch 22. Um, that being said, um, um, Unit 2 ultrasonic sensor. Now, we haven't even talked about Unit 10 yet, and we're supposed to talk about Unit 10 today. So, um, however, I was looking at our what's really left because we really don't have much left. We have Unit 10. We have 3 days left. The last day is our final, though. Um, and if we look at what we've got going on, we were supposed to do the Unit 10 content today as well. But there is time tomorrow to do the Unit 9 and 10 activities, which we've done most of the Unit 9 activities. The only Unit 9 activity left is the Roomba one. So I'll probably have you guys try to do the Roomba one on your own. And we'll try to go over that. So basically what you wanted to do is just drive forward until the bumper's pressed. And then you're going to do that random. Well, then you're gonna back up, and you can use spin forward to just back up like a couple of rotations, and then you're gonna use that random, like we saw on the slides, to turn a random amount, and then you kind of want to just put that all in a big loop, so that after it's backed up, then it's going to go back to going forward again until it hits something again, and then it's going to back up a little bit and turn. And so that's the general layout of that code. It's not super complicated. It probably is actually worth doing on your own, though. But if you're trying to look at how to do the random stuff, you can kind of look at the 9.2 slides, how to use that random number. Particularly, like if you look at slide 23. The only thing you need to remember is you do not need to do this SRAN thing. Are we still sharing, by the way? I
No.
am not sharing. Let me share my screen. Sorry about that. Um, so, like slide 23, here they're making a random number. In this case, it's just a random number between 1 and 10. And then they're using that random number to determine like how many turns they're doing, but they're using that movement function that they created. Now you don't have to do the movement function. You can just use something like, you can just let the spin 4 and use your random number as the number of degrees it turns in the spin 4 function if you wanted to. And just remember that you do not need this SRAN line of code. I was trying to select it, but it's a picture. That SRAN, the computer already does for you. But yeah, try tackling Unit 9 on your own. Not Unit 9, but the Roomba activity on your own. I would like to spend what remaining time we have left, though, to discuss a little bit about Unit 10. So Unit 10 and 11 are actually kind of optional units. Like you can just go up to the bump limit switch, and if that's as far as you get in the class, then that's fine. And in fact, I think there is a separate final that was made that's just covers up to Unit 9. So if you only get up to Unit 9, and that's as far as you get, then that's okay. And in fact, you'll see that Unit 10 and definitely Unit 11 doesn't actually have as much information in it. Like I don't think there's a homework for it. It does have a quiz, but there's not a homework for it. But let's look at the slides for Unit 10. So Unit 10 introduces the rangefinder. In particular, it mentions the ultrasonic rangefinder. But all this stuff that talks about the ultrasonic rangefinder, you can also use for the laser rangefinder. So, for instance, if you have the EXP kits, none of those come with ultrasonic rangefinders. Instead, they come with the laser rangefinders. But you can just use those instead. Be better anyways. These slides are taking a while to load.
Could you use a distance sensor as well?
Yeah, that's what the distance sensor is. Is the distance sensor is a laser rangefinder. So like if you're going to VEX code, and you're adding a device, yeah, that distance sensor, that's the laser rangefinder. That's what that distance is. But if you're trying to add a ultrasonic, you have to go into 3-wire, and it's the rangefinder here. Yeah, the distance sensor and the rangefinder, they both do the same thing, and they both basically have the same commands you use too. When this Chromebook gets too many tabs open, it starts chugging a bit. So here is an example of a robot that has, and with some big beefy 5-inch wheels. You can't even buy those wheels anymore. And this is actually, you can tell it's an old robot because it's got the old Cortex and not the V5 brain. But it's got this ultrasonic rangefinder on the front, and so some things about that ultrasonic rangefinder. So it sends out a sound wave, and then it bounces off and comes back. When you plug it up into the brain, it's actually got 2 wires to it. And I think it tells you when you're hooking it up or when you're setting it up what. So, for instance, if I'm trying to set up a rangefinder and I'm picking it out, it says to put the output in first and then input in second. And so you have to pick a pair of ports And you can either pick A and B, or C and D, or E and F, or G and H. So you have to pick one of those pairs when you're using the rangefinder. Right now, I can't pick A or B because I'm already using them for those bumper sensors. So if I could pick C and D here, but when you're hooking it up, one of the wires is marked output, and the other wire is marked input. And you want to make sure you get those right. So the output has kind of an orange. It's more of an orange wire, and the input's more of a yellow wire, but it says it right on the rangefinder. So just make sure you plug in the output in the lower slot. If you hook them up backwards, it won't work correctly. And also, and this is true of the bumper sensor as well, and the limit switch. But anytime you're plugging something into those 3-wire ports, you need to make sure it's plugged in until the plug is all the way flush. Because oftentimes the kids will be trying to do something and it's not working and they don't know why. And it's because they don't have their sensor plugged all the way in. So that's supposed to be plugged in all the way until it's flush against the brain. And so when you're using the rangefinder, it will it can you basically just it basically just returns a value, and that value can either be in inches or millimeters. So since and basically a rangefinder is just 2 speakers. Well, one of the speakers is acting like a microphone, and the other one is acting like a speaker and sending out so one of them sending out the sound pulse, and the other one's listening for that sound pulse. And since it is sending out a sound wave, it kind of sends that out kind of more of a cone instead of straight ahead. But some areas the microphone picks up better than others. So just like how any microphone has kind of like a range where it detects sound better, that's also true of the rangefinders. And in particular, it kind of makes out this kind of cone. And as we can see here, this goes all the way out to 10 feet. And this kind of shows the range of detection here. So your best bet for detecting something is going to be within about the 5 to 7 range, and about, what is this, about like 20 to negative 20 degrees maybe, or 15 degrees. That's going to be your best range of detection. And of course, the closer you are, the higher the angle you can kind of pick up. And then if you're going super far out, then it's really only kind of going to be picking out straight ahead. And so the rated range for these is approximately about 115 inches. So that's just under 10 feet. But as you can see from this graph up here, even out to 10 feet, it might not pick up super well. So the way we use it is we just like how we can so just how we can say like left motor position and then get to degrees, we can say something like rangefinder distance, and we can either put that in inches or in millimeters, and it will return a value in inches or millimeters. And so it does have a minimum distance, which is a minimum of 2 inches, and it can reach out to 115 inches. Or in millimeters, it's from a 30 to 3,000 range. So here's a sample code here. So it says if the rangefinder distance is less than 400, then we're going to stop the drivetrain. And that's in millimeters. So that's relatively close. So basically, this is saying, like, let's say we were already moving the drivetrain. Say we had drivetrain forward. And this is actually probably the first time we've seen drivetrain used here. But a drivetrain is a really super easy way to set up your robot. If you want the robot to move quickly as possible, instead of like turning all these motors or motor spin, you can really just set up a drivetrain. We've been making this whole time. We've been making you guys do it the hard way. But at this point, they might have earned the right to use drivetrain. If you want to let them use it at this point, because they probably earned the right to use it now. But it's really easy to use. Like for instance, if I want the drivetrain to drive forward, I can just say drivetrain. What is it? Drivetrain. I don't even remember the can because I never use it. It's not go. it's something. We can look it up later. But you could. I think it's like drivetrain drive forward, and then you just say how far you drive forward, or how fast you drive forward. I don't know. We can look at it later. But the drivetrain is really, really easy to use. Okay, but anyways, in this case, this code basically right here, if the drivetrain was already driving forward, then as soon as it when it checks it, if it is less than 400 away, then it's going to stop. So this would kind of prevent you from running in a wall. So you could literally make your Roomba code, but replace your bumper with the rangefinder. And in some ways that would work even better because you're not having to worry about the robot like running into things. And it doesn't have to physically touch the wall in order for it to back up. And so here's some code here. So they have this fancy function here. It's called ultra movement, and it's got a fast speed, a slow speed, and an ultra distance. So it's taking in 3 numbers here. And it looks like it's doing this, and this is our auto straightening code. So we're feeding at a fast speed and a slow speed. And the last one is the distance. And that distance is going to be our rangefinder in inches. So basically this is saying, like, say if we fed in like 50, 45, it's going to be auto straightening using like a fast speed of 50 and a slow speed of 40. And then it's going to go forward until it's 5 inches away from the wall. And then it's going to, once it's at 5 inches away from the wall, it's going to kick out of the loop and then stop our motors. So that's an example of it happening here. This is kind of like this is using if statements. It's not using an if else, if else, but that works too.
So does that mean it's running all 3 of those conditions continuously while in the loop?
Yeah.
And not like prioritize?
Yeah, it's not it's going to check all of these conditions every time. Yeah. So when you have ifs without the elses or ifs, just ifs by themselves, it always checks the ifs. Yep. So this is going to check all 3 every time. Which, as we've talked about, is not the most efficient way to write code. And so, once again, this was our fast speed, this was our slow speed, and this is how far away the robot needs to get before it hits the wall. On the final, you guys actually, for your debugging part, one of the functions that it has is something that's very much like this ultra movement. And so able to look at what the parameters are doing to be really useful for you guys. And so so Monday we're going to go over things for what's going to be on the final, and we'll probably do that a little bit in the morning on Tuesday too, before you take the final. Just and we'll go over what you need to kind of look for and stuff on that part of the final. So basically, with that code, if it's above that threshold, it's going to move forward. If it's below that threshold, it's going to stop. So if we were 10 inches away, then it's going to go forward. If we're 2 inches away, then it's going to stop. That's kind of what all this is saying. Now, what if the rangefinder doesn't see anything? Like, for instance, what if it's like on this long hallway here and it's not picking up anything? Or we got like this soft blanket here that's not reflecting a sound wave back. Well, oddly enough, the reading you get back from the rangefinder when when something's too far away for it to detect, it's not like it doesn't give a 99999 back. Instead, it actually returns a -1. And which is kind of weird, unless you know a little bit about how way computers work and how numbers work, like with binary. The reason it returns a -1, it's something called a overflow. Because when a number is stored in binary, instead of having like a ones place and a tens place and a hundreds place, like we do with a decimal number, instead it stores a number as like it's got a ones place and a twos place and a fours place and an eights place. So it goes up by base 2 instead of base 10, like we're kind of used to with our decimal numbers. And so and also we store the positive or negative bit as our very, very last bit on the end, or the or the, I guess you would say the very, very first bit on the end is going to be our sign bit. So if that's a 0, that's a positive number. But if that bit's flipped to a 1, that makes it a negative number. And so what happens is, as you're getting bigger and bigger numbers, that's filling up more and more of the bits with ones. And so eventually, if the number gets too big, it will fill up that signed bit that's on the front, and that will flip it to a negative. And so if the number gets too big, it will overflow into the sign bit and give you a negative number instead. And so that's why that ultrasonic sensor will return a -1 if object's too far away. And so if an object's too far away, that's going to kind of affect our inequalities there. Because, like, for instance, if I wanted to move forward until it's less than 10 inches away, well, in this case, it's returning a -1. And it's going to say, well, -1 is less than 10 inches away. I need to stop. But in reality, it has so much more to go. And so what we need to do is we need to, when we're setting our conditions, just like how we had like an and an or in our conditions for checking our left motor position, right motor position, we kind of need to set up a compound position where we're checking that if it's less than our target value, but also greater than -1. We need to so as long as it's less than our target value and also greater than -1, then we still want to then that's when we want to stop. So this is just kind of a review of those compound conditions. But ultimately, what that ends up meaning is we actually want, when we write our rangefinder condition, we want to write it like this. We want to write it so while it's less than 5 inches away, or while it is greater than 5, that's what it's saying, while it's greater than 5 inches away, or while it's less than 0 away, because if it's less than 0, that means it's returning at -1, then we're going to want to run the loop. So this time, instead of using the and, we do want to use the or, because we want to keep on going while either one of these is true, not just when both of them are true.
And we couldn't just use absolute value of the distance.
I guess that's also, I don't think I've ever considered that before, but yeah, I guess that is also very true, because the only time it's ever going to return a negative number is when it returns that -1. That's actually a much, and you're, like I said, I've been doing this for a while, and you're the first person that's ever suggested that. But I do not see why that wouldn't work, because it would flip the -1 to a 1, and 1 is going to be probably inside your target value anyways, because it can even read 1 inch away. I think it had a minimum of 2 inches.
Well, but
So
then wouldn't that make you stop? Because it would be less than the prescribed distance.
oh yeah,
So that would be the reason that you couldn't use it.
yeah. Okay, so there is a reason why we can't just use absolute value. Yep. Because 1 would be within your, yeah. Yep. Yeah, so we can't use absolute value. So there was a reason why we didn't just do that. Okay. All right. Thank you, Josh. So at any rate, when you're doing your condition, this is how you want to do it. That 5 is your target distance that you're trying to approach. So in this case, it's going to go forward until it's 5 inches away from the wall. But you also have to take into account for if it's too far away, you're going to get that -1 value. So so that's why you also have to have an or this. And by the way, oftentimes you would see this statement written all on the same line of code. It's just kind of done here, so on a separate line, just to make it kind of fit better. but this might usually you would see this kind of written out like as one big kind of line of code here, like these 2 lines. And that's all we have to say about the rangefinder. It's really, really, really easy to kind of swap out, like for instance, the condition for the Roomba code. If your condition before was while the button's not being pressed, instead you can replace all that with this condition instead, while the rangefinder is greater than 5 inches away.
Yeah, I think
And
the time-consuming part of this particular thing would be swapping out the sensors physically on the robot.
yes,
Yeah.
yes, indeed. However, there is if we, what is our activities for 10? I think 10. Let's take a look at these real quick. Okay, this is an optional activity. It's a really cool activity. So this is assuming that you have a rangefinder mounted in front of a robot. But it's to write a program so your robot will maintain a distance of 10 inches away from an object in front of it. So you can actually write a program using that rangefinder. So like if the robot is behind you and you move away from it, it moves up to you. So that, and then if you move towards it, then it backs up, and that so that it always stays 10 inches away from me, which is pretty neat. And in fact, for the final project that I do with the kids is they do a robot parade at the end where they kind of decorate their robots like a Mardi Gras float. But then each robot they put a like red plate on the back of their robot. Well, they use one of the big metal plates, and then they put like a red license plate on the back, and they use a combination of the rangefinder and the vision sensor to follow the robot that's in front of it. So you would have one robot in the front that you could drive around, and then all the other robots should follow that lead bot. And so if the and so what you can do to control the distance away is you can use the rangefinder, and then to kind of center the robot to control the turn of the robot, you can use the vision sensors where it can track that red license plate. And so, and then and since we're a K through 12 school, what we usually do is then we parade them down the elementary hall and kind of do a parade so that all the little kids can watch, and they get a big kick out of that. So that's what I usually do for my final project.
And then you
But
add the pneumatics to shoot beads.
Yeah, you could do that. And it doesn't have to be a pneumatic to shoot beads. You can
Or a flywheel, I guess.
well, yeah. Or you can make a catapult, especially if you use like a slip gear or something for a catapult. Band it back and launch it.
Some kid's gonna lose an eye.
Yeah. I'm making a requirement that it has to do some sort of other motion, whether it's like moving some sort of other decoration or something like that.
Yeah, you can have like a flag that they could like whenever like if they paused, like noticed it was paused, then it would raise the flag. And they could do that either with an arm or an elevator.
Mm-hmm. And yeah, if I have kids like raise flags, some of them did simple things like just spin a pinwheel or something. But and I have had some kids that have set it up to like throw stuff. There's no more ambitious kids did stuff like that. So it was kind of neat. Um, and once again, it just depends on how much time you have at the end, because by the time you get to the end of the class, end of the year, when you have finals and testing and all that, you don't have nearly as much time as you think you have. But this hill following you around is pretty neat. And in fact, you can kind of ride it all. You can ride it as a proportional control. That'd be the preferred way to ride it, where you have your target value of like say 10 inches, and then your error is just going to be like how far away it is from 10 inches, and then you can control the speeds of the motors based off of that. So just like how we're comparing the right and left motors for error, instead it's like how far away are you from that target value of 10 inches, and that could be your error, and that could control your speed. But it is a really fun once the kids get it to work, because literally they can set it up so the robot just kind of follows them down the hall. So that can be a lot of fun. Okay, so that's what's here in the, okay, so did we look at the other activity? Yeah, we did. Or no, we didn't. What's this one? It says using your existing drivetrain, add an ultrasonic sensor, create a code that drives the robot forward until the ultrasonic sensor is 5 inches away and then stops. Honestly, that activity seems too simple in a way, because that's literally almost what this code is. The only thing that's missing is like a stop, the motor stop at the end. But that's what this code does. So that might be too simple an activity there, because they could really just literally just write this code. Okay, so but that's ultrasonic sensor. There are interesting things you could do with it. Like I said, units 10 and 11 aren't. There's not as much stuff out there, but you can always come up with your own stuff too. Like for instance, that optional activity, it was something I added at one point, simply because I thought what was there wasn't enough. Any questions about that ultrasonic sensor? And everywhere where we said ultrasonic sensor and rangefinder, you can use the distance sensor to do the exact same thing.
Or the optical.
Optical sensor does not work like that. The optical sensor, it will detect if an object's in front of it or not, and it will even tell you the color. It'll even tell you the color of the object, but it does not detect distances.
You could use it for the grade route, I guess.
Yeah. So the optical sensor, like for instance, like this year with the Vex game this year, what you'll see is a lot of teams use their optical sensor to. Well, actually, last year, in fact, my team used the optical sensor last year, for when they were picking up the rings to like if they picked up the wrong colored ring, it would kick the ring out. And basically, as that ring came up, it looked at the color. If it's the wrong color, it kind of did a little jerk to the feed of it, and that kicked that ring off, so it didn't like score onto the goal. And so that's one place where you see the optical sensor used a lot to detect like what color object you got.
For
Yep.
people who don't have the vision sensor to do both.
Yeah. Well, okay. So the thing about the vision sensor is that vision sensor is probably providing too much information, because that vision sensor will not only detect objects, but it can detect multiple objects. And it will tell you where each object is. So, like for instance, when you take a snapshot of an object, it will or basically you take a snapshot of a signature, and that signature is a certain color value you're looking for. And it will tell you like how many objects are in that it sees that are that color, and it will tell you the positions of each one, and it will give you the X and Y values of the size in the screen. So it feeds a lot more information than you probably need. So like using a vision sensor to detect objects that are really close, it's probably a bit of overkill. And also, you also have to consider that since it's doing all the information, the refresh rate of that vision sensor isn't nearly as fast as the optical sensor. I think that vision sensor is like 60 frames a second, I think. So, and sometimes when you're feeding objects, you're moving faster than that 60 frames a second. So it might not catch it in time, like it's already passed by the time that vision sensor picks it. Yep. Well, I think that's it for all I wanted to talk about today. We did cover 10. We didn't spend a lot of time on 10. there. So if you guys think you can write a Roomba code, I would. You'll also have time to work on it tomorrow, from it looks like. But if you could write a Roomba code, and also if you could write a code to maybe make it follow you, if you put an ultrasonic sensor to stay a certain distance away, we can also work on that tomorrow as well. But that's what we're going to look at, because I pretty much ate up all the asynchronous time today too, and for that I apologize. But we did get a lot of that code done too. So it was a long day today. Does anyone have any questions about anything we've gone over today?
I don't have any questions about what we did today, but I do have a question about like the schedule going forward.
Okay. Yes, because you're not going to be here.
Yeah,
at all.
Tuesday I have AP Summer Institute. So
Did Vanessa say anything about?
no, I never got an email back.
Okay. So so that's so what? Because currently, as you probably noticed, that the class folder doesn't have the final in it right now. So I don't have access to the final right now. So so typically, but the final is set up as a Google form. Is basically what it is. It's just two parts. The first part is constructor part matching. The other part is constructor response. Did I say multiple choice and matching? And the other part's a constructor plot. But it's just two Google form quizzes basically. Is what the format of the final is. And what Vanessa's done in the past is that last day she's just posted it in the Google Classroom for you guys to do. And generally on that Tuesday, we'll do a little bit of time like just reviewing over things first, and then you just take the final. Is typically how that Tuesday goes. So in your case, Ashley, maybe we can get Vanessa to post it maybe Monday instead, so have it posted already. And maybe you might want to do it like Monday afternoon after we're done with the lesson, since you won't be able, because it sounds like you won't be able to do anything at all Monday because of Tuesday, because you're hopping into a whole different training, right?
Yeah. Yeah, I really don't want to miss on Tuesday, but it's kind of hard to miss the first day of AP training too.
Yeah.
So I don't know.
Yeah. So really all that's going on Tuesday is we're just going to do a bit of review and then take the final.
So my other question was, I see you on Monday and Tuesday.
Monday.
Oops.
Yeah, let me.
I'm sorry, it seems like my internet's cutting in and out.
Yeah, it's you're breaking up a little bit.
I was wondering, are we doing this final project?
You're doing a final project. It doesn't have to necessarily be one of those. So for instance, we could just say that your Roomba robot is your final project. That because in case you only made it to Unit 9, then the Roomba the Roomba project is your final project in that case. So but if you can just pull off the Roomba thing, that can serve as your final project. Or if you want to get fancier with it, you could try doing something else for a final project. And tomorrow we'll look at that folder, and it has some ideas for our final project. But really that final project is kind of up to you what you want to do. And there's a couple of examples in there, like I think the robot parade examples in there. The one Vanessa has posted is kind of like an obstacle course, kind of like a maze, um, but they don't know the final layout of the maze until the day of. And so the idea is for them, so they know what things they'll have to do to solve the maze. Um, and what they have to do is they have to, leading up to the final project, they have to create functions, like say maybe a function to do like a 90-degree left turn, or a function to go forward a certain amount. But then on the day of, they only have like 10 or 15 minutes to piece together those functions in order, like, so they won't see the final maze until that day. And they'll come in and then they'll have like 10 or 15 minutes to solve it. Uh, and what they're supposed to do is piece together the functions that they created in order to solve that maze or perform that task.
I think Ashley's trying to look for clarification about what we as teachers in this class have
Okay.
to do for a final project. Like, are we supposed to video that project, send in the code, upload that to Google Classroom? Like, what is the necessary requirements that we need to put in? Is that what you were trying to ask, Ashley?
Yeah, because I really can't add anything else to my robot.
Okay.
I don't have any more parts. I hardly have anything, and my principal's literally leaving school right now. So
Okay. So in that case, but you have those sensors, right?
I do have the sensors.
Okay. So, your your final project could just be the Roomba bot, okay? So, and what I mean by the Roomba bot is a robot that drives until it bumps into something and then turns around a random amount.
Okay, so I don't have to have a conveyor
'Cause
system.
no, you don't have to. That's an optional thing to do. That's if you have more time with the kids and they want to build something. You don't have to put a conveyor on that. Um, so
Okay, thank you.
and to demonstrate that, yeah, you could do like Josh did, take a video of it and upload a link to that video or upload the video, and then also upload your code for it. And that would be a demonstration of your button.
Okay, thank you. I was just kind of confused about what we were supposed to do.
Yeah. I think, yeah, that was more helpful. I think that clarified that.
Okay. Sorry, I wasn't answering correctly there. Um, and that's also true for the rest of you guys too, unless you want to do something with the vision sensor or whatever, and you happen to have it, you can. But if you don't want to go that far with it, you don't have to. Yeah. So, for instance, if you just want to use what time we have left to kind of shore up and reinforce the skills we've already learned, but we'll at least look how to set up code to do the vision sensor and and so forth. So okay. So I guess that leads us tomorrow. Tomorrow, just looking at the schedule, we'll discuss the final project. You'll work on your 9 and 10 activities and answer individual questions, and you'll work on your final project, which once again could be and what else do we have here? It mentioned something about exit tickets. I haven't seen that come up before. It says individual task, create exit tickets for units 7 through 10. Okay, I mean that's something we could do tomorrow as well.
Good deal.
Okay. I'm actually supposed to go to my classroom tomorrow, so I'll be teaching out in my classroom tomorrow. I don't know what condition it is in, because I haven't seen it since they waxed the floors. Um, but I'm supposed to have some of my robotics team members come in tomorrow. They wanted to do some stuff, so maybe I can show you what my classroom looks like if you wanted to know a setup. Okay, well, it's 1 o'clock. I think we learned a lot today. Hopefully, it wasn't too overwhelming. But we'll see, I guess. So try writing a Roomba code, and if you have the ultrasound sensor, see if you can make a follow code. And you'll also have time to work on that tomorrow too. Okay. All right. Well, I guess we'll end it here then. Take care, everybody.
Just a reminder, tomorrow I won't be on the Zoom call again. I'll be traveling again.
Oh, okay. All right. Well, and the video will be posted. And thanks for taking time out while you're off site to join us.
Has she gotten to compete yet?
No, she throws today at it'll be 7:15 in Central.
Okay. So I was gonna watch later tonight. So, what happens if she makes the final?
Well, if she makes the finals, they do it like the way they do it
2
for
days?
javelin. It's the same, like all at the same time.
Oh, okay. They just show the film. I got you. Okay.
Yeah.
Okay. Because they won't show the final until I guess to what is today? So Saturday maybe.
I don't know that they just do all parts of it then, and they
Okay.
just they don't always show javelin anyway. So
Right. I got you. Well, good luck.
all right.
Rooting for her.
Yeah.
I made a Quizlet for I don't know what's gonna be on the final, but I just kind of took like everything that is on the homeworks and I just put it on a Quizlet. Can I share that on the Google Classroom?
Sure. You if you want to share the link in one of the comments or something, or
in the stream.
I think I can make a post.
the
Yeah.
stream. Yeah.
Okay.
Yeah, you can
Thank
just
you.
share that in the stream. Yep. And I'm going to see if I can dredge up an old final somewhere. so to let you guys have a better idea of what's on it. Yep.
Does
I
it
think when
change
I go
every
to
year?
school, I think I might have a paper copy of it. Not really. No, I don't think it's changed in a while. There's actually probably some things that need to probably change on it, but nope.
All right. I'll see y'all tomorrow.
Okay. All right. Everyone's gone.